All right, so next unit, unit 4 is digital multimeter. So now we'll call that the DMM. So if I say DMM, you know I'd be talking about this. But sometimes they're also called a DVOM. Anybody guess what this means?
Volt.
You got it, Ronnie. That was close enough. Digital volt ohm meter. So back in the day, we used to have a voltmeter, an ohm meter, and an amp meter, and there were 3 different tools, and then they kind of combined them. So DVOM was like a big common term, but technically like a more modern meter can do more than just volts and ohms and amps, and so DMM is more standard. So when we say DMM, this is what we're talking about. This one happens to be a fluke. You may use a different type, but it is digital, which we'll cover a little bit more, but digital generally as evident by like a LCD screen, not a needle. If you see a needle, that's not digital. That's a whole different game right there. So we're going to cover how to use it, like all the features, you know, how to put it in the right mode, how to interpret it, but then also circuit testing. Circuit testing, we do a little bit up front, but then the part 2 is going to be a lot of the circuit testing, like how we test a series circuit is a little bit different than how we test a parallel circuit. And so at least 2 parts of this, it might even turn out to be more. All right, so without further delay, the DMM, the DVOM, I think we're good. An electrical measuring tool frequently used to diagnose and repair electrical faults. So if a vehicle came in with, let's say, a headlight in op, yes, you may just slam a bulb in there, and if it fixes it, cool. But if it doesn't, this is going to be your next step right here. You could probably use a test light and mostly figure it out too, but at the point, you know, the test light can tell you some things, like basically tell you voltage, but it doesn't give you a number. It gives you like the bulb lights up. So the really preferred method would be to go right for this. This can tell you everything you need to know, but the test light could still be a valuable tool as well. And then once we get a reading, so you do that, you're going to learn how to use this right now extensively, and you're going to get readings. But once you get a reading, it needs to be this word, interpreted and applied. So you could in 5 minutes learn how to get readings with this, but the real work is for you to understand what the reading means and what you should do next, right? So we've done a little bit of electrical. If I were to take these leads, the positive, negative lead, and I were to connect them to the light bulb socket, you may say, like the connector, and if I were to get 12.6, that tells me everything I need to know. But do you know what that means?
You got good ground.
Good positive and good negative if I probe it right at the bulb, right? So that's like the most basic application of the understanding. There's going to be a lot of other things along the way. So if you were to do a voltage drop across a headlight switch, you know, you should be able to take the measurement, yes, but then you need to also know, is it a good measurement? Is it a bad measurement? Is this a measurement where I found the fault? Is this a measurement where the switch checks good and I need to continue diagnosing, right? So a lot of the work is learning the theory so that you can apply it. A little bit of the work is simply learning how to use the meter. Cool? And then that has to be used in conjunction, like along with knowledge of electrical theory so that you could diagnose whatever the circuit is. The circuits vary, you know, and sometimes the way we go about one circuit is different than the way we go about another circuit. So right here, this is a big chunk, and that's why we started to cover so much of the theory already. And in some ways, I did really think about just getting you out there, getting you to do some measurements and stuff like that, but you'll have no idea what to do with those measurements, right? So this is what we're building up to. Cool. So as we go, it's a DMM because the meter gives a numerical reading. So the numerical reading would be like, let's say I turn this on to volts, and you guys will see there's a number here. That's why it's digital. It's just some digital readout. Cool. An analog meter uses the needle. So that would be like, hold up, we don't use these. There's a couple reasons why we don't use them. It's not to say they're not good tools. But as we get a little bit in there, they're going to talk about like impedance, which is kind of a different word for resistance. So if you're measuring circuits on a modern car, you know there's a good chance it's going to have to do something with a computer, right? Computers all over the place. Well, these are really computer friendly. This has like what we call a high impedance. It has a high electrical resistance. When this has a high electrical resistance, that means if you make some connections and you unintentionally provide a secondary path for electricity, it's not a big deal because this has a lot of resistance, so that means a little bit of amps. You remember that volts, ohms, and amps? So if you have a lot of ohms, there's going to be a little bit of amps. Computers are fine with a little bit of amps. The problem with these needle ones, like an analog meter, that's what they'll call analog. So from now on, if I say analog, we're talking about the one with the needle. Those don't necessarily have a lot of internal resistance or impedance. So if you do a test on a computerized circuit, you just made basically a secondary path for the electrons to flow. If they have not a lot of resistance, that means they can make kind of a lot of amps. Computers don't like when they try to flow a lot of amps through them. They let their magic smoke out. You understand? The smoke comes out and the computer doesn't work. The only way to get the computer work again is if you get all the smoke in there, get all that smoke, and you get all that smoke back in that computer, and then in theory, I think, I'm joking, right? You'd burn it. You'd fry the computer, if you will. So that's why this is a yes. Ones with needles are a no. So like, I went over to my dad's house and I was setting up this off-grid solar thing because I'm going to get them all, hooked up. And I'm like, I forgot my meter. Do you have a meter? And he busts out this thing with a needle. And I'm like, oh my gosh, I've only read about those. Like, I don't even see those. Where did you even get that? So you're not going to see one with a needle unless it's like somebody got it at the swap meet or, they found it in the trash type of thing. It'd be probably pretty difficult to even find one that you could purchase. It's all gonna be digital. Digital's the go-to. Now you see why digital's it's better in every way, except it costs more, but not that much more. Cool, so let's just say, and again, the analog meter, if we had an analog meter, it wouldn't be a volt, an ohm, and an ammeter. It'd be a voltmeter, an ohm meter, and an ammeter. So you have 3 different meters with the needles, cool? So if it's a digital, it can at least measure AC current, DC current, voltage, which is both AC and DC, and AC and DC amperage and resistance. So that's why it's your basic a basic DVOM. A DVOM can do all those things. If we call it a little more modern terms, a DMM at a minimum is going to be able to do that, at a minimum. But then it might be able to do some more stuff. So like this is a Fluke 87. This is a bit of an older meter actually, but this is pretty top of the line. This is like an industry standard. If you see the yellow with the gray, that's probably your clue that it's a Fluke. Fluke is just a good brand name. This one can do a whole bunch of stuff. Like there's a whole bunch of different functions and features on here. For example, it can measure frequency. But your basic meter might just do volts, ohms, amps, basically, in AC and DC. Cool, so as we get more, let's say, here's that Fluke, but this is actually a slightly different version. This is kind of what came before the 87. So on here, you've got a whole array. This one is a little nicer and newer. This one's a little more basic. This one's fine. I don't even exactly know what that one is. That one may be like a Centec or something. So you may get, a $20 or $30 DMM from Harbor Freight or Amazon. They sell them at Home Depot. The ones at Home Depot tend to be a little more like construction oriented. So if you buy a meter from Home Depot, when you turn on, it's probably going to default to starting on AC. So every single time you're going to have to change it to DC, except in the unlikely occurrence you actually are going to measure AC alternating current, right? So these would all be, general meters that could be used on a vehicle. Sometimes the advice would be, if you get a meter that's kind of like the standard that everybody is going to use, it'd be nice. And back in the day, this was it right here. So I'll never forget, my shop foreman made fun of me a little bit. I was looking at these meters and the Flukes were like $400. And the Flukes could do a lot of stuff, but then there's a brand called OTC. OTC, they make a lot of automotive tools. And it was an automotive specific meter. And what was really cool about it, it had a bunch of little features like for example, this is actually a little inductive amp clamp. It could plug into there. It had what's called Noid lights built in. So with that OTC meter, I could actually have an injector Noid light tester. It had a lot of cool features. And I went for it. I was like, and it wasn't any cheaper than the Fluke at the time, like just maybe $50 cheaper. But I went for it because I thought, hey, this one could do even more. And then I remember I was testing a problem on a car, and my shop foreman, you guys remember the function of the shop foreman? If you got a problem car and you're really struggling, the shop foreman is like top technical dog in the shop, may come alongside you and help you, right? So as I'm testing it, I got all my tools out. He comes over and he wants to double check a measurement. He goes to turn the meter on and he pushes the power button. It doesn't turn on. He's like, "Is your meter work? Is this thing dead?" And I was like, "No, press the button." And he pressed the button like this. It doesn't work. And I was like, "Oh no, you gotta hold it longer." And he's like, "Oh, it's a press and hold." And then he was kind of irritated and he was kind of like, "I think it's time for a new meter." And I was like, "I just bought it. Like, it's not even 6 months old." So I probably wouldn't say that was justification for me to go to the Fluke, but now you can kind of see, like, if everybody's familiar with this and you go with some off-brand funky meter, cool, that's on you. Especially if you save the money, that's great, because tools have one job, and that's to make you money, right? So if you spend more money on the tool and it doesn't make you more money, you're kind of wasting money. At that point, you're just collecting toys, and they are pretty neat. But if you need help and you call the foreman or me over and I don't know how to use your meter, you know, that's kind of frustrating. And they might say something hurtful like, "It's time for a new meter," when the meter's brand new, okay? So consider all that. Here's your analog. That's pretty cool. You see this needle? Ooh, you know, they were neat. They were visual. Not going to use this commonly. And a little detail inside the meter, like this one as well. They have specific types of fuses. They're fast blow fuses. The reason for that is if you put the meter in the wrong orientation and you make a short, you want that fuse to blow quickly rather than the wire to burn, or, you know, it's made to basically sacrifice itself. However, those fuses can range $10 to $20 each. So that's something to consider. You don't want to not know what you're doing, but also, you know, if you got some weird off-brand meter and it's got a really weird fuse and you can't get a hold of a fuse, you need to keep some spares. The reason I like that OTC though, it had a basic glass style fuse and you could buy a whole bunch of fuses cheap. I think that was one of the reasons that OTC was, you know, saying this is an automotive based meter. We know you're going to blow some fuses. You can get them cheap, but consider all that. But it is special. They do have a 9-volt battery. Typically it's a 9-volt inside, sometimes a little different. And then if you look right here, this is just showing, this is what we call a Cat 3 meter and lead. So when we talk about these, Cat 3 is a voltage rating. So Cat 3, 1,000 volts, Cat 4, 600 volts. Why would we even care? Like, that car shouldn't have potentially 600 volts, should it? A regular car, no. This one, for example, Cat 3, 1,000 volts max. This is an amazing meter that could be used. An electrician could use this, but on automotive we could use this. But back in the day, this was overkill. It's not overkill now because hybrid electric vehicles can have 600 volts. They can have over that, by the way. Even a Prius can be 650. Some of the EVs run an 800 volt architecture. So when you hear the difference between if it's a Cat 4, 600 volts, that may no longer be enough. If it's a Cat 3, that's 1,000. But there's one detail that almost nobody really goes into. If you look at this picture, You notice this lead looks kind of weird? There's only a tiny little bit of metal probe showing. That's what it takes to be Cat 3. So like this meter right here is good for Cat 3, but these probes are not actually. So this meter would kind of be actually dropped to a Cat 4. This is only really good for 600 volts. Even though the meter says 1,000, these leads are not. So if we were to dig around, they might even say on them. But almost all the time, you need to have this little sleeve on there. Sometimes you could take them on and off, by the way. But sometimes modifying or making it easier to work with actually lowers your rating. Cool. So a couple things about the meter. And then if it's a good meter, it could measure frequency. So that's what I was saying, like that Fluke can do frequency. That cheap Centec on there, I don't know. Maybe yes, maybe no. Frequency is a pretty basic function. It might. Temperature sometimes. May even have a dedicated diode test function. So if you guys remember, I gave you a little sneak peek last week about a diode test. This one, for example, it has it right there. So if you guys look, there's volts AC, volts DC, millivolts DC, ohms, but then as like a submenu, there's this thing that makes it beep for continuity test. And then right here, there's actually a diode test. So if you want to test a diode, it needs to increase the voltage it's putting out when you do the resistance test. And you could test it this way and then reverse polarity, right? So if you have a meter and it doesn't have the diode test function, that just means you can't test diodes. Do you test diodes every day? No. But you kind of want a tool that's going to be able to do the job, every job. Otherwise, you're going to have to, you know what you have to do if your meter won't do a diode test and you need to go test a diode, right?
You have to get more tools.
You got to buy another meter. So now you got 2 meters and you probably didn't save money. You probably lost money, right? Or if you're in a shop with other people, you go to somebody and say, hey, can I borrow your meter? I need to do a diode test and mine doesn't do it. You know what they're going to tell you? It's probably time for a new meter. So these are hurtful things. This is something my foreman said to me when I was, I think, 19 or 20 years old. Probably 20, we'll say. Because if I was 19, I wouldn't really be diagnosing the car myself. I might have been right around 20, maybe 21. That'd be right after community college graduation. I was feeling pretty good. And this guy came and said, it's time for a new meter. And I was like, oh. I still have the scar. There's no physical scar, but he said something hurtful to me with a brand new meter. Cool. And so, again, fast blow fuses inside. The DVOM and test leads should have a Cat rating listed on the front. So like 3 would be the preferred. If you got a Cat 3 meter with Cat 3 leads, you're chilling. If you have to measure things higher than 1,000 volts, let me know what you're working on because it ain't automotive. Cool. And that's really for safety, right? So when you talk about measuring circuits, if your meter is within the rating, it's keeping you safe. If your meter is only good for 600 volts and you're measuring 800, that's when you may not only damage the meter, but you may actually find yourself being electrocuted. Cool. And then if you don't have the meter with a sufficient Cat ratings, could result in injury. Remember, it's not designed for use on high voltage circuits, so check that out. Make sure you're getting a meter that'll do all the things you need. All right, and so this was, again, Cat 1 is electronics. That's like low power stuff. Let's say that you're working on, well, in this example, a copier or like a PC type of part. They're not high voltage. Cat 2 would be like a single phase. So that is, the typical, you plug it in the regular outlet. You could do Cat 2. If you get into commercial stuff, that's when you're pretty much needing Cat 3. So if I were to simplify this, if you plug in a microwave to the wall, that's a 120 volt outlet, you're good. But if it's a commercial, like if it's a dealership or a big shop would be, generally that's commercial, right? If it's a small one, maybe not. But if it's commercial, some of those are running 3-phase like 480 volts. So if you're Cat 2, you're no longer good for 480, and commercial buildings can have 480. So that's kind of when we get into Cat 3. And then you could even go with like Cat 4. Sometimes they'll get into this if it's outdoor. And so Cat 3 and 4, we don't get super meticulous on, because if you've got a Cat 3 that's good for 1,000 volts in a car, you're good. We're not super worried about if you're doing utility work. That's like, you know, when you get a power outage and you see the people climbing the poles and stuff, they got a whole different outlook. They got different PPE, different tools, totally different job. Refugio, go ahead.
So the Cat 5 here on here has the one that says 600 volts.
Yeah.
But there's two different things. One for a 10A fuse or a 6 millimeter, a 6 mm fuse. Is that where we position them?
Yes, but I'm coming up to that. Yeah, it's okay. So we in a little bit we'll talk about all the different ports. So where you put your leads depends on what you want to do. Right. So as we go more, if you're let's just say to make sure that I'm being thorough on electrical safety, you're going to work on the hybrid EV, and that's going to be the 600. You know, it might be 240, 250, 260. For the battery pack, but when the inverter is actually putting out power to the motor, that's when you can exceed the 600. Okay, just so you know. If you're working on that type of system, it's important you wear certified and tested Class 0 rubber insulated gloves. So if you get really into the high voltage stuff, it's not just the meter being Cat 3 or 4. You know, the service manual, you'd always be referencing the service manual pretty closely if you're working on the hybrid EV system, and it's going to tell you, wear gloves for this, or it's going to tell you, you know, wear gloves until you measure that the voltage is 0, or like it'll be like below 1 volt, and then you can remove the gloves. Make sense? So if you see somebody working on a hybrid or an EV and they're not wearing gloves, it doesn't necessarily mean that they're wrong, although it might. If you see them go just right straight in without, you know, ever having worn gloves, they're probably taking some risks. But, you know, if you see someone who's a little bit more trained, like the way that I would proceed is I'd follow the steps to take the high voltage system down. I would put the gloves on, but I'd make sure they're tested, you know, so I may check the date. Sometimes I'll roll them and see if there's any air leaks. We actually have a tool you can put the glove on and pump it up to check for air leaks, because if there's a little rip, a little pinhole, that's a spot where the electricity could go through the insulated glove and into your body, right? So there's some safety protocol there. But I'd glove up all properly. Then I would put rubber gloves over the top. Why do you think we put leather protectors on top?
More insulation?
Not exactly. Protect the rubber, exactly. So you got these really strong insulated gloves, and then you work on metal parts, right? Don't you think the metal could cut the rubber? And now you no longer have the insulation. So the purpose of the leather is really just to protect the rubber. Cool. And I'll go and I'll do my measurements, and I'll disconnect my high voltage disconnect, or the service plug, sometimes they'll call it. And then I may wait a certain amount of time, looking at a watch that I don't have. Then with the gloves, I'll do a measurement, and if the measurement is good, the gloves can come off. Cool. So if you ever see a professional working on a hybrid with the gloves off, doesn't necessarily mean they're wrong. It just means they may have gone through the process to make sure. You can measure that the voltage is low, and then the voltage is low. You don't have to go around with your big mittens on trying to get a 10 millimeter bolt like this, like trying to, you know. But until you make sure it's safe, you do. Cool. And that's kind of what it's saying. They should be a little bit shorter, just to make sure that the leather doesn't touch your skin. Right? So it's supposed to be, the only thing touching your body should be the rubber, and then the leather should be on top of the rubber only, but the leather should not be touching your skin. Okay, that's one of the safety things. And then again, the DVOM has the instrument, which is, the instrument body is this, right here. Cool. And then you always have to factor the leads. So the leads should have a rating on them as well. So if you get a Cat, let's say 2, if you get a Cat 3 meter, but you put Cat 2 leads on there, that sucker is all Cat 2 now. Have a nice day. And then of course it has a function switch so that you can choose what type of measurement you're trying to do. So Refugio, that's kind of what you're saying, like what's this port do and what's this switch do? We're going to break all that down. And then typically the test leads are going to come in with red and black, but let me just make sure you understand. If I were to take the red lead and put it where the black one's supposed to go and put the black one where the red lead's supposed to go, the leads aren't special. They're just colored, that's it. So you make sure that you plug them into the right spot just so you know which lead is which, but the red lead's actually no different than the black lead except just color. Technically, you could do the whole job with 2 black leads or 2 red leads. You just got to keep track of which one's which. So there's those gloves. This is going to protect you from that high voltage. This is going to protect the rubber. Cool. Here's the dial. So let's go with the dial for a quick second. If you were to look at this, and let's say I were to turn the dial to here, does anybody know what that symbol is? That first V? Voltage, but I like that I heard alternating. AC volts or alternating. You notice how it goes up and down like this? Remember how alternating goes up and down? It alternates positive, negative. Boom, that's AC volts. And then you notice in yellow it actually says hertz. If you put it to AC volts and then you press, I believe it's this yellow button and this one. I think it's yellow or blue, but I'm a little fuzzy on that. That will cycle between AC volts and hertz, for example, because this meter can do hertz. Cool. So that's why sometimes there's 2 things on there. Then if I go up one further, anybody think they know what that one is?
DC.
DC volts, exactly. So if you want to measure voltage, right here, those are your options. AC, DC. Cool. If you guys have the meter, if you want, go ahead and see. You got some varying meters out there, so go ahead and pick out which one is AC and which one's DC. You guys get to see the fluke right here. AC or DC. That's it. Pretty simple. Pretty simple. If there's any more meters in there, I can't give you this one. This one's mine. Yeah. Get one more meter. You and your partner can share. Cool. All right, let's get on to the next one because look, there is an MV. What the heck is MV? And notice, it's a little m and a V. Interesting. Millivolts, exactly. So in a second, we're going to get into how to do the conversion from volts to millivolts. And you're not going to ever do this on cars, but you could do kilovolts, right? So if millivolts is measuring 1,000th of a volt, how would you explain that back to me? Like, why would you want to use that? Why would you guys ever want to use millivolt reading? I'll explain like this. It's almost like if you want to zoom in really close. So if you just want to measure voltage, you can measure voltage, but it's going to be like 12.6 or 12.5. If you put on millivolts, well, you wouldn't really want to put on millivolts at 12.6, but let's say you're trying to measure like really low voltage, like 0.030 volts. If you were to put it on millivolts, 0.030 volts would actually become 30 millivolts, and maybe it would show 31 millivolts. Makes sense? So the meter doesn't look all the way down to the milli level unless you put it on the millivolt setting. Make sense? Go ahead.
So does everything have some degree of voltage?
It does, but you have to kind of know what you're looking for. So if you're checking a battery, I put it right here on DC volts. If you're trying to check some instrumentation inside the computer, like remember we saw those printed circuit boards? If you're trying to check something with that, maybe you want millivolts, you'd have to put it on millivolts and then it's going to show you a reading in millivolts. But if you don't put it on millivolts, it's not going to read that exact, you know? So let's say that you had, I'll even write it. Let's say you're doing a reading of 0.001 volts. Of course, this marker is junk. Should have known. If you put that on volts, if you are trying to measure that's the actual voltage, if you put it on volts, your meter is going to read like this. It's going to say 0.00 because that's as far as it goes. So does it have 0.001 or not? You don't know because your meter is not on the right setting. Now, if you were to change over to millivolts, it's going to move the decimal point over here. It's not going to show this. It's going to show 3 millivolts. And or it's going to show 1. Sorry, I don't know why I came up with 3. I was tripping right there. It's going to show 1 millivolt. So if you're on the millivolt setting, it'll show actually a 1.0 millivolts. Cool, so it's just looking at a very, very small scale. It's kind of like if you were to, let's say you wash your own dishes, you take a plate and you look at it and you say it's clean, right? Yeah, put that sucker under a microscope and let me know. Makes sense? Millivolt setting is like a microscope. If there's any voltage as large as a millivolt or 1/10 of a millivolt, now it'll see it. Make sense? Cool, and then if you look, the next, so now we kind of understand the millivolts, and you can change between AC and DC. The next one is this one. Remember that symbol? It's called omega. Ohms, yeah. So why would you want to use that? Yeah, if you want to check resistance of something. A wire, a light bulb, We checked fuses the other day, remember that? You could check it with your meter checking voltage, but if you pull the fuse out and you put your leads on the 2 little legs on the fuse, you could put it on resistance, and that should read like a 0 resistance. It should be like a 0.2, something like that, right? So ohms. Now there's a detail right there that I'm just going to skip ahead. Most likely, your meter, and this one, I had pulled up, you'll notice that one of these, this one's actually volts and ohms, so that one's kind of unique. But a lot of the ones with 4, if you want to measure ohms, you may have to move your lead. So like on this one, actually ohms in the same spot on this. So that one's pretty nice too. Once in a while you gotta move them, but you definitely have to at least move the dial. Cool. And then right here, this one, I'd be surprised if anybody than Tim gets this, but this one has a weird symbol, 2 symbols. This is not something you're going to commonly use. And actually, this meter doesn't even have it, but this one does. So that symbol and that symbol, anybody got ideas? Somebody sees the diode. Yeah, that's true. I bet you your meters don't have that. This meter doesn't even have it, so don't feel bad. And then this one is a capacitor test. And then the next one, what's that look like? Yeah, so you want to check your temperature, get your meter out, put it on. Oh, does yours have temperature? Most don't.
Yeah, this one.
Does it?
It says C.
But you may need a thermocouple for that. Put it on it and see if it gives you a number.
64.
Oh, wow. Yeah, yours is working. That's cool. That has something that this one doesn't. So you did good on the power probe meter. But sometimes you actually have to buy another accessory to be able to measure temperature, and that's a thermocouple. You have to actually plug it in and then set it to that temperature. It'll read it. Cool. Which we have one. I just didn't bring it out. And then now we're down to these final 2. So let's cover the final 2 together. They're both A. One's one type and one's another.
AC, DC.
So it's amperage, AC amps, and if you press the button, it'll change over to hertz, or DC amps, which is a little bit more similar. Now, this one is almost always the case, but you'll notice you will probably have to move it move your lead to the A. If you look, this one was volts, ohms, capacitor, temperature. But if you want to measure amps, you gotta pull your red lead, move it over to amps. Anybody think they know why that is? If you can read really small right here, do you see what it says? 10A fused. If you're gonna measure amps, you really should have it run through the fused part of the meter. Makes sense? So this part, a lot of times they'll have like a really small fuse, or you could just, it may not work at all. But in this one, they'll have it fused. So more than likely the meters you have will be fused. So like this one, for example, if I'm on voltage, we're good. But if I want to move it on amps, it says right here, 10 amp fused. Cool. If I were to put it on milliamps, that's only a 400 milliamp fuse. So like on this meter, there's what sometimes we would call the big A and the little a. The big A can measure up to 10 amps before it blows the fuse. What happens if you connect your meter in series and it's over 10 amps? Blows the fuse, right? So and that happens sometimes. If it's over 10 amps, you don't really need to measure that amperage. There's other ways to measure that amperage. There's other ways to even calculate that amperage using Ohm's law, right? But if it's under 10 amps and you want to measure it, cool. That's why the 10 amp is fused for you like that. Makes sense? But if you wanted to measure milliamps, like let's say that I was saying it could be up to 10 amps, right? But if we're checking for a battery that drains itself, we're not looking for amps. We're looking for like milliamps. We're looking for a very small measurement. You could put on the milliamp function. The problem is, like in this meter, it's only fused to 400 milliamps. That's 0.4 amps. So if you have half an amp, that's blown. It blows a different fuse in here. Makes sense? So you got to be familiar with your meter. You can see there's kind of a lot to know about the meter, which is why it's nice. If everybody had the same meter, we'd all be familiar with it. But if you hand me your meter, I'm going to have to look at it for a bit and be like, let me check this out. I even saw a meter. Mac Tools makes a meter where when you move that dial, you remember that, well, I'll show you on this one. When you move this dial, if you put it on volts, it has a piece of plastic and it blocks off the amp port. The reason they do that is because if you accidentally have your meter lead left on amps, remember that goes through the fused part. And if you try to measure a battery voltage, measure source voltage, that's going to try to flow all the amps through your meter and that fuse is going to be annihilated. So if you were to try to put it on volts, it won't let you because it's blocked by your meter lead. Or if you were to put it on volts first, you won't be able to plug your meter lead in. So it's kind of neat. It actually blocks the ports off. But that's kind of like it's dummy proof, and I can appreciate the dummy proof, but I'm going to say I don't think you should need that. You shouldn't need those training wheels. You shouldn't need, remember you go bowling and they have the bumpers up, bumper bowling? You shouldn't really need that. That's for little kids. So if you're a little kid, then you get the meter that blocks off the stuff so you can't connect it wrong. But if you're all grown up, I'm expecting you to be able to know where the lead should be and where the setting should be when you turn the knob. Cool? We were right here. Now I'm gonna make a little stab here at this meter. Remember, because I got stabbed, now I get to stab. That's the rule. This meter is called auto ranging. This meter's not. So if you guys can see these, I'm even gonna turn the lights off because I know it's a little hard to see. Can you see all these different settings? 1.5 volts, 9 volts, 2 volts, 20 volts, 200 volts, 600 volts. This is all to measure volts. And then it's off, and then 600 AC volts, 200 DC volts, ohms, 2,200,000, 20,000, and 2,000. Like, where do you want to put this knob, this selector? Where do you want it? Kind of depends, doesn't it? So this would be my thing. What are you trying to measure? If you want to measure battery voltage, you want to set this up where it's above the maximum, but not by that much. So what's battery voltage typically? 12.6, right? So which one, if you can remember these numbers, which one would you set this to measure a battery? DC, direct current. And here's your options again. 2, 20, 200, 600. 20, yes, that's exactly right. So if you set it to 20, it can measure up to 20 volts. However, if you set it to 200, it'll measure it, but it'll have the decimal point in a kind of like, it won't measure it real precisely. It may say 12 volts, but it may not show the 0.6. You know, I'm not 100% familiar with this Amprobe DM7C. You know, to me, like, if you need my help on a car and you bust this out, I'm gonna be like, no, this ain't happening. Fixing the car and diagnosing electrical problems hard enough. I don't need to use brain power on a meter that's like, looks more complicated than it needs to be. Kind of makes sense? So now I understand why the foreman stabbed me. This is a dude with tons of skill, tons of experience, tons of qualifications, and I come down here and I try to teach an old dog new tricks and be like, check out this new OTC meter. And he's like, get the fluke. I don't have a fluke. Time for a new meter. Man, that was so mean, but I'm kind of like, now I understand him a little bit better. Makes sense? Like, it's not necessary for me to have to really, it wasn't that hard though, right? 20 volts is pretty easy, but I'm just saying, most automotive technicians are going to be irritated if you have some cheap thing like this and you'd be asking for help. Cool. So I like to keep it simple. Now we will talk quite a bit of difference about the auto ranging and non-auto ranging. But before I do, if you buy a meter and it comes with a bunch of accessories, that's a good thing. So like, for example, that's the amp clamp. This is the thermocouple to measure temperature. Here you've got your meter leads. They have the Cat 3 little tip caps on there. And also you got a couple of alligator clamps. When we get into probing, I'll show you even more. So if you wanted to test a wire, I'm gonna tell you the bad ways. You could get something like this, where if I squeeze this, I put it on the wire and then I let it go, it pokes the wire for me, and I can get a real quick, easy measurement. You know why I'm gonna tell you no, no, and no? What did I just do to the wire insulation?
It cut.
I poke a hole through it. So if I poke a hole through it to get a measurement, what happens when some water splashes on there? Yeah, and so that copper is going to be kind of corroded and oxidized, and it's only a matter of time before, yeah, you took a measurement there, but it's only a matter of time before that's now corroded and you have a big voltage drop there. Makes sense? So a lot of these are nice and they're trendy. Like, you loosen this one up, you put it on, you probe it. It's a whole bunch of pokey things, and no. That's not professional. That's a no. That's a no. And like remember I told you it took me a long time to diagnose that car that had the inoperative headlights, and I told you I had to pull the bumper off the car, Pontiac Sunfire, I still remember. Okay, do you remember why that wire was no good? Because wires don't just fail. Wires are usually, you know, maybe they're rubbed or burned or cut or bitten or chewed by those mice. Do you remember why that one had failed? It was all corroded inside? Yeah, exactly. Remember the previous tech, when they did the recall, cut the plastic conduit off and they pierced the insulation. It took actually years, but that wire failed, right? So now I want to introduce you to these. And when you buy the meter, it may not have these, but if you're gonna do this, you're gonna have to get these separate. This is a back probing tool. This is very small. You see how small this is? The difference between this, like this one looks small to your eyes, but with electrical terminals, this is scary. Like, you ever go and get a mani-pedi? Don't lie to me. You ever gonna go and you're gonna get one, if they bust out like the chainsaw, that ain't the spot. You know what I'm saying? This is the chainsaw. This thing electrically is like, oh my gosh, put that away. If you're gonna try to back probe that, you're gonna be bending terminals and stuff. Now look at this. See the difference? This, we should be able to go right through the back probe, not stab the wire, but slide it into the terminal and take a measurement like this, right? Now we're gonna spend quite a bit of time on how to back probe, but I just wanna show you, this is a good accessory to have. So you do a little adapter, and now this one is adapted here, and this is your careful, this is when the nail tech busts out the file or whatever. I have actually not had that done, I'm happy to say. But, you know, they break out a file, you're like, oh yeah, that's good. And if they break out a grinder, it'd be like, ooh, I might lose a whole toe. You know what I'm saying? So consider that when you get the meter. If it comes with a back probing kit, that'd be great. Cool. Now, I'm going to teach you something about metric. I don't know how much of this you're already familiar with, but in fact, I did a little bit of this in the basic auto class. But everybody needs to be semi-familiar with this, because this will make you misdiagnose the car, and I'll prove it to you. Cool. So here we're looking at the basic symbols, so I'm going to write a little bit different. We're going to do like, well, I call the base unit right there, and that's going to be K, H, and D, then nothing. D, C, and M. You've seen these before? No, because they don't teach you this stuff anymore. I don't really know why. But you can see this on screen, or I go too far to the left. Okay. K is kilo. Okay. So I'm going to teach it to you in a way I think you'll understand. H is hecta and deca, but we don't really care about these. Okay. So just we'll lightly like say, don't worry about those. This is nothing. And then I think this is deci, and we don't really care about this. This one, just for the record, if you want, is centi. Anybody ever heard of centi?
100.
Centimeter? Yeah, right? Technically, if you really wanted, you could measure centivolts, but I don't know that anybody does. And then this one, actually, I really should have made this one a small m. Is milli. Okay, so let's say you're working on a vehicle that's Japanese. What's your most common socket size that's always lost?
10.
10 what? 10 meter? 10 meter? This is 2 meters. Give me a 10. It better not be a 10 meter socket. I don't know what you're working on with a 10 meter socket. Millimeter. Right, so now if we were to just talk about distances for a moment, let's make this one a meter, okay? Meter is just the meter. It's not the millimeter or the kilometer, right? I'm going to say it's kilometer, cool, but I'm going to say kilometer just so you remember. We call this the prefix. The K is kilo, cool? So if I'm saying a meter, you guys know how big a meter is? Show me with your, how much? How big? How big? Yo, you're going to tell me in feet and freedom units, aren't you? And I can appreciate it. Okay, 3 feet. So if you know what 3 feet is, look at your feet, right? It's about this, a yardstick. Might even be like this, right? That's a meter. Somebody show me a millimeter.
Thousands of that.
All right, so let's break that down. If you have a meter and that's 3 feet, and let's say you have a 1.0, I think I'm going to run this marker, but I may change it up. If you have it right here and you want to know a millimeter, let's count the spots. Ready? 1, 2, 3. So we go 1, we move the decimal. Ready? 1, 2, 3. We put it here, put the zeros here. This becomes a comma. Can you see that's 1,000? So there's 1,000 millimeters in 1 meter. So if you told me a meter was this, what's 1,000 of this? A millimeter's like this, like this. Make sense? Now let's go the other way. If we had, let's just say we switch our number. Let's make it, we'll keep it at 1. Cool. 1 meter. How many kilometers is in 1 meter? It ain't gonna be 1,000. There's 1,000 millimeters, yes. But you know, this way we could go 1, 2, and 3. So we take our decimal point like this. 1, 2, and 3. Put it here. It would be a 0.001. Makes sense? So you have like basically practically nothing. It'd be 0.001 kilometers. Makes sense? That's kind of crazy. Let's give it a different, let's do it a different way. Let's say I had 1,000 meters. How about that? Anybody know this answer? The decimal's right here. Would you agree? If I have 1,000 meters and I want to go to kilometers, you got to move it 3 decimal points. 1, 2, 3. You know what it becomes? 1.0 kilometers. Cool? The metric system does make sense.
No, it doesn't.
Oh yeah, it do.
Sometimes.
So 1 kilometer is 10,000.
1 kilometer is 1,000 meters. That's a comma. And then this is a decimal, so let's just eliminate that one because we don't really need it there. Cool.
There's no metric on the moon.
I don't even know how to respond. All right, but that's how you do the whole calculation. So like the way that I came through school was a little different than how they do it now. We did cursive too, but they also taught me this. It was called this. Kids have dropped over dead converting metrics. And we had to convert metrics in every kind of which way. All sorts of metric conversions. But let's just say, and I'll make one final point. You see the centi and milli? If you had a 10 millimeter socket, that's a 1 centimeter socket. So if you want to make a joke with your friend, be like, hey, can you pass me the 1 centimeter socket? And they'll be like, huh? 1 centimeter is 10 millimeters, just asking for it in a different way. Cool? Now with that being said, let's eliminate all this. And let's focus on what we really need to know, which is in electrical, it's really just going to be kilo, nothing, no prefix, right? And milli. Let's make it, I don't know, what do you want to do? You want to do volts? You pick volts, amps, ohms, what you want? Amps, okay. Amp, right here. Amp. Let's say I had 1 amp. How many milliamps is 1 amp? Do you remember how we did that? Let's be a 0, 0, make it a comma, make it a decimal point. So isn't that 1,000 amps, 1,000 milliamps? Okay, so if you're trying to use your meter and your meter auto ranges to milliamps and you see a 1 on there and you think it's a 1 amp when in reality it's a 1 milliamp, do you see how those are not the same? Those are not the same at all. So you got to be able to understand how you do this. The other thing I'll say is on the ASE there's at least 1 to 2 questions where all you need to know is this. I'll give it to you an example. The spec, let's give it a spec right here. The spec is 0.8 to 1.2 kilo ohms. You see that symbol, right? Then it'll give you answers. It'll say, which one of these is in spec? A says 700 ohms. B says 70 ohms. C says 1,100 ohms. And D says 1,400 ohms. Don't answer this right away. But does this even sound like an automotive question? No. This is like a basic dumb, I think it was 5th grade when I learned it. I know because I remember the teacher, if you were caught sleeping, he'd throw the marker and he threw it hard. And if it hit somebody, because it had chalk on it back in the day, it wasn't whiteboard, it was chalk. When it hit somebody, poof, big old poof of white. So I'm pretty sure that was 5th grade. This is where we learn this type of stuff. So on the ASE, they're asking me stuff I learned in 5th grade. I think it was, I don't even remember what type of science they called it, but it might have been 6th. I think it was 6th. 5th grade, I think it was earth science. Whatever. One of these is right. Who knows what the answer is? Is it 700 ohms? Is 700 ohms between 0.8 and 1.2 kiloohms? No. So let's make this. How about we take this kiloohms and we make it into ohms? How do you make this into ohms? You got the 0.8, right? The 0.8 kiloohms is over here. How do we make it into basic ohms? What, did I write that D? It's supposed to be
3 times backwards.
Okay, we're at kilo, so if we want it this way, we got to go 3 to the right. So we go like this. 1, 2. Okay, 1, 2, 3. Isn't that 800? Yeah. Okay, but we need to do one more. See the 1.2? Let's do the 1.2. So 1.2 kiloohms to make it we're in ohms, right? Kiloohms. How do we do that? 1, 2, 3. So how do we do that? 1, 2, 3. Add the zeros. So is that or is that not 1200?
Yeah.
All right. So your range is 800 to 1200. If I told you this in cash, give me between 800 and 1200 bucks. There's only one of these that's between 800 and 1200, okay? There you go. Ding, 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 ding. That's really all they're asking you. But they're going to ask you in electrical terms. Ohms to kiloohms, kiloohms to ohms, amps to milliamps, milliamps to amps. See, so sometimes in the service manual, they may give you the spec in kiloohms, but you may have a measurement that you performed in regular ohms. You just got to be able to move the, it's always the thousand though. So kilometer is big, right? So if I say 1 kilometer, how many meters is that? 1 big kilometer becomes a lot of little meters, am I right? 1,000 of them. Make sense? We're always working on the 1,000 because we don't waste time with 100 and 110th and then whatever this is, 1/100th, 1/10th, and then 1/1000th, right? We're really working with kilo or milli, and that's it. So if I were to say meter, 1,000 meters is how many kilometers? We're going from meters to kilometers. It's going to be a smaller number. Cool. So 1,000 meters would be 1 kilometer. If I were to say 1 meter is how many millimeters?
It's like a million?
No, it's only 3 decimals, right? One meter becomes 1,000 millimeters. Cool. 1,000, yeah. This is 1,000. This is 1/1000th, or this is 1,000, and this is 1/1000th, if that makes any sense. So 1,000 millimeters is the same as 1 meter, which is 1/1000th of a kilometer. Kind of weird, huh? You gotta be able to do that every which way, okay? So let me junk all this, and then we'll do one with amps was fun. We had amps, cool. So if I had an amp reading of 1.2, who thinks they can tell me how many milliamps that is? I'm going to move the decimal 3 digits. You all agree with me on that, right? The question is, am I moving it this way or am I moving it that way?
1,200, right?
You're right. How'd you do that?
Move it over to
1, 2, 3. Boom. There you go. 1,200 milliamps. Cool. Now, what if I were to say I have 0.2 amps, and I wanted to know, yeah, again, how many milliamps is that?
that'd be 200.
Yeah, 200. Exactly. Cool. Now, what if I were to say I had 17,000 amps? And I want to know how many, not milliamps, I want to know how many kiloamps. I don't know, I guess that's a thing. Okay, so we take the decimal, right? Which way do we move it?
Move it over to
That way, huh?
17.
Yeah, 17. Yeah, exactly. 0.0 if you want, or drop the 0. Exactly. 17 kiloamps, I guess. Which I've never heard measured, but maybe that's a thing. Cool. So you can slice this and you can dice this anyway. Sometimes the way we're doing it, we don't start here though. Sometimes we start over here. So if I were to say I had 32 milliamps, I want to know how many amps that is. So we got the 32.0, right? And I'm here. How do I get here? How many amps is 32 milliamps? 1, 2, 3. Exactly. So 0.032. We could add the 0 here. Exactly. Cool. It could take some practice, but if you generally get the understanding, we're cool. Now, if you're still struggling, I'll give it to you in another way. Let's say that some of you are on some kind of medication, like Michael was sick. Let's say he had to take some Tylenol or something. How How do you measure the quantity of Tylenol you're taking when you're sick? Milligrams. Okay. So milliliters, okay, you're probably,
Tablets?
it depends. I mean, but the point is, when you're talking about personal consumption, wouldn't you say it's something? Milligrams, milliliters, whatever. Cool. 800 milligrams. There you go. If you're, so when you're carrying your milligrams, that fits in your pocket, right? If you're dealing grams, that's not like a pill or two. Make sense? Okay, that means you're probably selling. You're probably got bags of it. Am I right? There's going to be 1,000 pills. If you're dealing in 10 milligrams, but you're actually dealing grams, you probably have 1,000 10 milligram pills. You ain't taking all those pills. You're selling them. Busted. Am I right? Who's dealing in kilograms?
The cartels.
The jefes. Exactly. So the big, they're not carrying a bag. They got a truck. The whole truck. The whole entire truck has kilograms. Okay, does this make sense? So if somebody says, yeah, I think he sold 1,000 kilograms, it'd be like, no, you have no idea what you just said. 1,000 milligrams, maybe, yes. 1,000 grams, maybe. 1,000 kilograms is 1,000,000 grams. Like, where'd you put all that? That's what I'm saying. Like, we get literally into the tonnage. Okay, so same with electrical stuff. If you're trying to measure a battery that goes dead over the course of a week, you're measuring really in milliamps. There's a milliamp draw on there. It's not going to be in amps, because amps would kill your battery like in hours. If it's killing it in days, it's going to be milliamps, right? So it's all on the scale. If you're investigating someone for personal use, you're looking for milligrams. You're looking for milliamps. Make sense? Yes? Kind of. Okay. Very good. Now, the reason we got so into that is because many times people are doing a measurement and they get a number and they skip a step. They forget to calculate the prefix. So now we know it's all sorts of very different. Right? Makes sense? All sorts of different. You have to see what the prefix is. You'll see some of these meters are going to say some of that. So like, for example, if you had, and the resolution's like how zoomed in it is. If you have a 0.1 millivolt, but you thought it was volts, 0.1 millivolts in volts is going to be like a 0.0001 volts. Make sense? If you thought the battery was charged, let's say you measured the battery, cool, and your meter flashed 12.3 on the screen. You think you're good, right? But what if it's 12.3 millivolts? 12.3 millivolts means 0.0012 volts. That's dead. That battery's discharged. Make sense? You can get a number and forget to check whether it's milli or kilo or nothing and totally misdiagnose the car. Cool? All right, so as we get a little bit further in, just remembering, like, if you have an electrical problem, you wouldn't necessarily go right for the meter, but you're probably going to go for the meter pretty soon. It's one of the first used tools if it's got an electrical problem. Cool, so we're going to measure the voltage, resistance, current flow, but you don't just start measuring random stuff. You have to have a specific reason you're trying to go there. So if a car won't start and you go out there and you turn the key and it just goes like click, click, it'd be probably a pretty good idea. Get your meter, measure the battery voltage. If the battery's dead, you know the car doesn't start, right? Right now you're thinking about jumping it and you're thinking about getting a battery and all that type of stuff. It'd be really smart to know what the battery voltage is. That's going to tell you if the battery's charged or not. Cool? Now the meter measuring the voltage doesn't exactly tell you like the details of the plates and the electrolyte level in the battery. It doesn't tell you even the cold cranking amp. So a battery tester will tell you a lot, but a meter will tell you if it's charged or not.
And it doesn't tell you the full story.
It doesn't tell you the whole story. It just tells you if it's charged or not, and that's it. Cool. And then, again, you have to know what you're testing. What do you want to test? If you want to test the battery for charge, what do you put it on? Volts, amps, or ohms? Volts. That's going to tell you the electrical pressure that's in the battery. Exactly. If you wanted to measure how difficult it is for the electrons to make it through a wire that happens to be off the car, what do you think you put it on? Ohms, yeah, it'll measure the resistance of the wire, exactly. Cool. So you got to know. And then if you're dealing with high voltage, that's when you get in the CAT rating. If you're dealing with resistance, the circuit needs to be disconnected. Now let me explain that to you. When you put your meter on ohms, like this, it uses its internal battery, which is a 9 volt, to send electrons through the circuit. So if you send electrons through a circuit that's still connected and the battery's sending its own electrons, don't you think you're going to get a crazy reading? Yeah, it has to be isolated and powered down. We've covered that a couple times, but just as a reminder. And they should be removed from the circuit. So like, if let's say that you wanted to test a switch, you'd actually want to disconnect the switch and then test the switch. It's not to say that sometimes you can't measure the switch while it's still installed, but you got to remember, if the switch is connected, there's other paths, right? It could go through the module or it could go another way, and you might get some funky measurements, and then you get yourself confused and you misdiagnose it, and it's real easy in an electrical problem to get what I call off in the weeds. You're supposed to be on this straight, narrow path that's like, you test this, if it's good, then you test this. If it's good, then you test this. Oh, it's bad. There you go. It sounds easy, right? But if you get off in the weeds, all of a sudden you thought the test was good, but it was actually bad, and now you're measuring something over here and the wrong thing, and then next thing you know, you've seen that meme, the meme, where the guy's hair is all crazy and there's like all these strings and stuff pulled and he's there smoking and he's like, that could be you real quick if you get off in the weeds. I'm gonna tell you right now. Sometimes I even do. Cool, so just keeping those things in mind. And then when we get to the meter, you know, they're talking a lot about connecting the leads to the right spot, depending on what you want to measure. And then of course, you got to set the correct meter range if you're using a manual range meter. And that's why I really like the auto range. I got to get the leads in the right spot, but then I just got to get this set to volts and it'll range it for me. Cool? Doesn't that sound nicer? If you got a manual range, that's that one you had to pick the 2 volts, the 20 volts, the 200 volts. Remember that one? Which one would you like, the auto ranging or the manual?
Manual.
You like the manual, huh? I like the auto. I'm okay with whatever you like, but the reason we covered that whole kilo milli is because the auto ranging it'll give you a clean number because it'll automatically range to that zone. So if you have a battery that had that 1.3 millivolts, it'll shoot up on the screen. It'll shoot up on the screen like, it might even say, let's say it had 0.012 volts. It might show 12.2, but it might be millivolts. Make sense? And you'll be like, 12.2, it's good. And you'll miss that it had the little m. Okay, so the auto ranging is amazing, but you have to look for the little m or the big K. If you don't, you're going to get a really bad number. And also you have to look for the big M, by the way. Like let's say if it's on ohms, a big M would actually be not milliohms, not kilo ohms, it'd actually be mega ohms. So mega ohms is like 1,000,000 ohms. Cool, so there's these little prefixes that are in there. The auto ranging is great, but you gotta pay attention. Cool? Okay, so for example, if you're trying to measure volts and you put on volts right here, boom, and you get 6.23 volts. Cool, that's a pretty simple, easy to understand, correct? Learning what you just learned though, what if I were to change this slightly and make this, see that little M? Do you think you could miss that if you're not being careful? So what's that number? 6,230. All right, so that's, again, we'd have to take the 6.23, and then you remember the milli was over here, so we'd have to go like a 1, a 2, and a 3. So that would be a right here, 6,230 millivolts to actually be 6.23. So if you're 6.23 millivolts, what that actually means, we do it the other way. I guess probably really how I should have done it. If you're trying to measure in volts and you're in millivolts, you gotta go this way. You have 0.0623 volts. That is not even close to 6.23 volts. Make sense? So you might see this number, but you gotta look for that. Cool. Kind of the good thing is you'd normally already know what you're going for. So like if you're trying to measure volts, you're already looking for the volts. If you see millivolts, it's way too low. Like you'd be like, oh, I've got 6.23 millivolts. Wow, that's basically nothing. That's like you saw what that was. It was 0.006 volts. That's dead. That's totally discharged. Cool. So just watch it with that. Or if you really hate all that and you can't possibly understand it, then get yourself a manual ranging one and you set it where you want it. You can do that. And by the way, actually, this can do manual range too. If you press the range button, it could change it to millivolts or change it from millivolts to volts. Cool for you. So you don't always have to do the math calculation. You just have to understand how different they are, right? And then different modes and the jacks like we talked about. Should be pretty familiar with these. So let's just say you wanted to measure voltage. You put the meter on volts, DC, and you put the red to the red and the black to the black. You think you can handle that? What do you think happens if you accidentally put the red meter lead to the negative terminal and the black meter lead to the positive terminal? It actually won't really be a big deal. Don't even worry about it. I've done it many times. You know what it'll show you? Let's say that battery's 12.6. You know what it'll read on your meter? Negative 12.6. That's it. You'll be like, negative 12.6 volts. Oh, I got them backwards. It's not a big deal. So flipping these leads is not a big thing. That's very different than if you go to jump a car with jumper cables and you hook the red to the black and the black to the red. I've seen cars get so messed up, they're totaled. I mean, so that, we're not talking about jumping the car, we're just talking about measuring it. Remember this?
Wires get hot when you do that?
On a number of different occasions, I've seen it blow a bunch of big fuses in the fuse box. I've seen stuff catch on fire. I've seen, I didn't see, but I heard of batteries blown up. I mean, there's some issues, a lot of issues. So jumping a car, very critical. Measuring, whoops, not a big deal. Don't even worry about it. All right, now this one, we're gonna skip. If we're gonna measure resistance, can you see how we do it? We put it on ohms right there. It's gonna show us ohms. You put the one terminal here, you put the other terminal there. And remember, it's gonna use its little 9-volt battery. It's gonna send electrons out here and see how hard it is for them to come back, and that's gonna tell you the electrical resistance. Is that easy enough? Where's this component right now?
Inside the computers.
Yeah, but how are we testing it? The best way to test it is with it removed. Can you see how they kind of took it off? If you want to really test the circuit for resistance, you need to isolate that component. So let's say that you wanted to test a wire. To test a wire, the best way with the least confusion, you disconnect the wire, you test from the beginning of the wire to the end of the wire, and that's it. Now sometimes I'll cheat and I'll test it in the car because it's hard to disconnect the wire or whatever, but you just have to understand, if you're measuring, let's say that you were trying to measure the resistance like this is pretty simple, but a lot of times it's going through a computer and there's different circuits and whatever. Those electrons will find a way, even the unintended way, and that'll throw your number off. Make sense? So removed is gonna be better. Do you think that you can handle measuring voltage and measuring resistance? It's pretty simple. All we did was move the selector just from volts to ohms, and then you're good to go. Now this one's different. You will screw this one up. Remember I told you I got that brand new meter? I did okay at my first dealer, but you know, a lot of people in automotive, you know, were maybe a bit autistic, I would say. I'm sorry, I'm saying it for me then. You're not autistic, I'm autistic. I wanted a raise. So rather than go to my supervisor, she was kind of a jerk actually. I'm not even gonna lie to you. But rather than go to her which I was a little intimidated of her. I should have just sat down and said, hey, you know, you hired me for real numbers. You hired me at, I think, $6 an hour, and then minimum wage went up, and like I was pretty much minimum wage-ish, but I was an apprentice, you know, so when you're being trained, you're not expecting to make a lot. Cool. But then I did 2 years of community college, passed a bunch of ASEs, spent $8,000 in tools, and then I graduated, and you know what she hit me with? Big raise, $13. I was at $13 an hour. This is 2006, so like not apples to apples, but still. And the thing was, at school, everybody's number that they wanted was $18 an hour. It was like, man, I'm gonna get 18. I'm like, 18, I'd be balling, you know, that'd be huge, that'd be awesome. I want it. So rather than sit down and talk with the manager and say, hey, I feel like this is where I'm at, you know, because at that point I had graduated, I was no longer an apprentice, I was on the line, diagnosing, fixing cars. Sometimes they kicked my butt. I wasn't really that good at it yet, but I was a little prideful. I had the toolbox, you know, I was ready. So rather than sit down with her and say, hey, 13 is not really what I feel I'm worth. Not, I need $18 an hour because I'm looking at that CBR 1000. I want that bike. I saw the commercials. I saw the commercial over and over, and I'm going to get it. And I could buy that bike brand new for $8,000. No, $9,000. Like, that's not relevant. What was relevant is I've graduated. I'm on the line. I've passed these X, Y, and Z tests. I'm fixing cars. My productivity is pretty good. I think I'm worth more. She'd have given it to me. I know that now, but I was 20 years old, so I was kind of and a little autistic. So it's kind of a ding-dong. So instead, you know what I told her? I'm going to go back to school. You know what the real truth was? The dealer down the road gave me an offer at $18 an hour. I didn't tell her that. I was like, oh, I'm going to go back to school. I was too chicken to say, hey, free market's a double-edged sword. You can pay me whatever you want, but I could take whatever I want too, and they're going to pay me 18, so I'm out. Bye. What would you guys say? Bye, Felicia? Yeah. That wasn't her name, though. But but she probably would have known. No, that's true. So instead, I lied to her face, told her I was going back to school, but I really took a job down the road. So when I went down there, you know, I was the new guy, and I had some of the new tools, and this place was a little bit more in the hood, which is probably why they were paying more. They couldn't get a lot of people. And it was a Pontiac dealer, so they were kind of dead. There wasn't a lot of business. But I remember I had that brand new meter. Remember that meter I told you about, that OTC? Well, a line tech down the way was like, hey, and they called me boy. Hey, boy, can I borrow that meter? And I didn't take offense to that. You know, they were saying that because I was young. And I'm like, yeah, you know, it's a good meter. Well, he's like, your meter doesn't work. I'm like, it definitely does work. So this was a certified line tech that I thought, and he's smart, but I thought he was like super smart. He borrowed my meter to measure amperage. Cool. He handed me back my meter broken. Luckily, it was only the fuse. How did that happen? Well, I'm going to tell you. The way we measure amperage is very critical. If you want to measure amps, you need to change the position of the lead. You got to move it from the V to the big A. Make sense? From the V to the big A. Big A says 10 amp fused, okay? But the next step is, if you want to measure how many amps are flowing through the circuit, you have to open the circuit up and insert your meter in a way where the electrons are going to go through your meter and then continue through the circuit so it can count them. Make sense? I knew that because I was fresh out of school. I know that now because I think about a lot of the stuff we're about to talk about, like for the day or two leading up to this, so I'm kind of on my game, right? But this dude had been out of school for 20 years. It's pretty rare that we actually have to measure amps, but he needed to measure amps on this blower motor. He went under there with the meter leads. Let me set myself up so I got them. Right, here's my meter leads. You can see the colors. Let's say this one's red, this one's black. And he was like, he did this. Now I want you to think about that. If he did this, what did I just do? Not exactly, but I guess I should clarify. I'm going to draw it. I'm not drawing on this thing today. He didn't disconnect the circuit, I guess is what I was trying to say. He left it like this. You can see this is red. So when he did this right here, my body's my meter. Where'd the electrons go? the electrons went right, they're like, forget going through this light bulb that has 4 ohms or 8 ohms. It was like, let's just go through the meter. Pow. When the meter is in amperage setting, because you move the lead, that has no internal resistance. If it had internal resistance, it would mess your measurement up, right? You can't measure amps, but add resistance because that's going to lower the amps. So when you're in the big A, that meter has no resistance. So if you understand my body being the meter has no resistance. In fact, I got the meter right here. I'm going to use it. Cool. I'll even put it in the correct slot. Here's the meter. If I do this, didn't I just give like a direct path through the meter and the meter has no resistance? So how many amps are going to flow?
12.6.
That's volts. Think of the amps. I got 12.6 volts. I have 0 ohms. There's no resistance in my circuit at all. Freaking pshaw, everything. Total. All of it. And my meter went like this. You know what it did? Eee! Like that. The smoke came out the fuse.
What size fuse is in these?
I don't know. You got to take it apart. On this one, it's 10 amps. I can guarantee you if you have no resistance, it's going to be like as many amps as could possibly flow, probably limited by the wire size because that's going to get hot really quick. If it's not fused, it catches fire. So he was like, boy, let me use your meter. And I'm like, sure, it's a great meter. Meanwhile, I'm thinking like, I hope he doesn't come back to me like my foreman did, tell me it's a piece of crap and time to get a new meter. Instead, he's like, yeah, this meter's great, but it doesn't work. Here you go. See why I'm a little funny about letting people borrow stuff now. So boom, when you measure resistance, or when you measure amperage, you have to open the circuit like this. See this? Now the electrons can't go around the meter. They have to go through the meter. This is called putting the meter in series. You have to send the electrons through the meter. Or if you don't, and you measure it more similar to how you measure volts or how you measure ohms, you're going to overload the circuit in the meter. You will blow the fuse. Okay, which isn't really that big of a deal. But remember how much I said the fluke fuses cost? 10 to 20 bucks. So that's $10 to $20 mistake. How many of those are you going to make in a day? Right? You just that was the cost of your lunch, and you just blew it on a blown fuse. And that's probably a pretty good lunch too. Now you eat nothing, no soup for you. So that's how you're going to measure it. This is the one that bites people. Okay, so I'm showing it, trying to be really clear. I try to tell you the story mainly so you know, as full-fledged line technicians, people still screw this up. Once in a while, okay? So watch it now. Cool. And then again, AC volts, DC volts, millivolts, if you're trying to look at the millivolt level. Cool. Ohms, which includes a continuity test, which is kind of nice. I can actually even demonstrate that. If I'm going to measure ohms, I put it to here, right? But you notice I left my meter in this spot. It's kind of mad at me. Can you hear that? Okay, because like, hey, you're not supposed to be there. Here it's happy. So that beeping was your first clue. If I wanted to measure in ohms and put that beepy sound on, first off, let me just show you. If I touch meter lead to meter lead, what do you think it's going to measure? Can you read it or no?
0.
Too low? Or can you read the number? Too low. Okay, here we go. How about now? I don't even know what it should read about 0, right? 0.2 something, 0.1. That's good. That's low resistance. But if I want to do a continuity test, I could press a button. Just have to remember which button. Might be blue. Oh, here it is. Sound. Okay, so continuity test is really the same measurement as resistance, except, look, ready? Touching, not touching. No continuity, continuity. So if you're testing a wire and you put on one end and the other end, if the wire's good, what should you notice? Beeping. If you try to test the wire and it's no beeping, the wire's open. If it's beeping, the wire has continuity. You could still look on the screen, but the continuity test is just kind of a way to get you a sound. See how the sound's gone, but the numbers don't change. But the sound is kind of nice, especially if you're under the dash, twisted, and your eyes are closed because you're pretending that you're on a sunny beach. That's why you're yelling, sunny beach! And you're like this. and it says beep. You're like, all right, the wire's good. Get me out from under this dashboard. Make sense? Continuity test. Diode, milliamps or amps, but a lot of times if you're going to go to the measure actual amps, that's when you got to go to the big A because that's fused for 10 amps, typically. And then this symbol right here is different. Anybody know what this is? It's called like mu or muth or something. So you remember how we had the kilo, the base unit, and the milli? All right, way big over here is the big M. That's mega. That's a million. So if it was, I'm going to keep it electrical. If it was ohms, there'd be ohms, kilo ohms, which is 1,000. Mega ohms, the big M, is a million. And then in the other direction, there would be an ohm, ohms, and then there'd be 1,000th is a milliohm. 1/1,000,000th is this, microamp, micro-ohm. So if you see this symbol, this is micro. Micro is 1/1,000,000th. Make sense?
So is it 3?
6.
6?
Exactly. 3 would be milli, 6 would be micro. 3 would be kilo, 6 would be mega. Cool. So some of the high-end meters can measure down to a micro, which is 1/1,000,000th. 1/1,000,000th.
What would you use that for?
If let's say that we are trying to test a hybrid asynchronous AC motor and there's 3 phases and you want to know the difference in resistance on the windings between U and V and W and U and W, you could do 3 measurements in a milliohm or a micro ohm, and you could tell, like, is the winding starting to burn, or like, is the winding getting high resistance? For general automotive, don't worry about it. But for like high-end electric vehicle motors, maybe. And actually, to be quite honest with you, you wouldn't even be using this tool. They have some really precise, very specific milliohm testers, and the milliohm testers are going to be what you'd actually use for that. But it's still. I want to mostly get you to be familiar, so you're not like, what the heck? I didn't learn that in school. So probably, if anything, I'm giving you more than you need. Cool. And then here's your reading. So what's kind of nice big display. It says right here it's DC. It's volts, right? So how much is this?
12.
12 volts, exactly. 12 millivolts? No, because it doesn't say millivolts. If it was reading in auto-ranged millivolts, that's when we'd have that M right there. Right here. So if you saw a little M, that would make it millivolts. Cool? So just double check that it's a V and not an M or a K, right? If it was kilovolts, it'd be like this. Cool? And then sometimes they'll even like give you a little range button. So if it's in the range, it's measuring basically between 0 volts and 10 volts essentially, or in this case really 40. So it'll give you, it's mostly a visual. I don't pay a whole lot of attention to that one. What I mostly need to know, if it's in volts range, then I know this is 12.00 volts. Whereas if this was in millivolts and it gave me 12 millivolts, that's really 0.012 volts. Yeah, you like it, you love it. Cool. And then this is kind of what we were saying. Like this one has the K. So that 10 volts or that 10.00, what's that actually measuring? I show a 10. So is this 10 volts? No, heck no. This is 10 kilovolts. So that's 10,000 volts. Don't touch that. That could be life or death. You're just not going to see 10,000 volts on a car, so don't be that scared. But if you're an electrician like a lineman or something, you're measuring something on the big high voltage, high tension lines, you could see that. Cool? You guys kind of get the K pretty good? All right, very, very nice. And then OL. So this one, you know, I already previewed this a bit, but this is not overload. although one of the books shows it as overload. Overload to me is like you overloaded the system. The meter's been overloaded. It's dying. So I don't like to call it overload. It's out of limit or over limit. Which one you want? It's up to you. Over limit, out of limit. That means the same thing. So if we were to look at, let's say, DC volts, and this is auto ranged, or maybe you put on manual, and it can read up to 4 volts. If it's over the limit, what do you think that means? Because it can read a maximum of 4 volts. So if it's over the limit, how many volts does it have? 5, 7, 3,000, 17 million. It's over 4. That's all it means. Over limit means it's over the limit of the measurement. It's out of the limit of the range that it can see. If you put it on a manual range, you can go 0 to 4. That's it. So I would just leave it on auto range. If you leave it on auto range, it's not going to show OL. It's going to show, if it was 5 volts, you know what it would show? 5.0. Cool. So manual ranging is all right, as long as you know for sure what your range that you want is. Cool. So my recommendation, leave it on auto ranging, but just pay attention to the little prefix. If it's millivolts or kilovolts or mega ohms or whatever you want, or micro, which you won't see much of. Cool. But let's say this is resistance. Let's say if you put this on ohms. This one's something that will bite a lot of people. Matter of fact, I'll do it with the meter right now. So if I want to measure ohms, you remember I put the meter on ohms, right? Click, 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 boop, boop. There, I'm on ohms. Cool. If you guys can see, I want to do the backlighting. There we go. Here's the backlighting. All right, I've got this meter on ohms and it reads OL. What the heck does that mean? In layman's terms, essentially that means it's an open. Do you know why it's an open? They're not touching. How do I make it not an open? Now what's it read? Yeah, that's good. Cool. Now let me break it down for you. In fact, actually, this one showed it pretty well. This is showing ohms, but it's actually showing a big M. What's the big M mean? Mega means million. Yeah, million. Million. Big M is big. So like there's big M, mega. Kilo, still pretty big. Kilo's 1,000, mega's 1,000,000. Not the little m. See, that's one thing I could say metric kind of screwed that up. Like, why you have a big M and a little m? You should just have different letters. But I didn't make it. Makes sense? So,
Well, it kind of helps because when you look at it, that means I'm going this way.
yeah, okay. All right. The cup is half full. I get it. So the big M over here means million. So this is looking for how many ohms? How many ohms when it says big M? Looking for millions of ohms. Big M is millions. So if it's looking for mega ohms, that's millions of ohms. If I see OL, what's that tell you practically?
Out of limit.
It's out of the limit, and how high is the limit? Millions. Yeah, not even 1 million, but millions. So let's just say there's trillions of ohms. You know what this will say? OL. It'll say OL. It can't do trillions because it only goes as high as the big M is millions. Cool? So right now, maybe there's I don't even remember numbers bigger than that. What's the biggest number you know? Million? Billion? No, billion is smaller, and then trillion?
Quadrillion.
Quadrillions.
Quintillion.
I knew you would know.
Quintillion.
Except, stop it. You just, if I said like pi, I want 3.14. You just gave me 3.1415268, and I'm like, stop. Like, okay. So if it's millions of ohms, and that's all it can see, if it's got quadrillions or hectabillions or whatever you just said, it don't measure that. You know what you get? Oh well, I'm out of my limit.
A Google class.
I can
A Googleplex.
All right. I don't. Did you just try to sell me on crypto?
No,
I'm not doing crypto, buddy.
1 followed
Yeah.
by a Googling
It's
of
10 to the 100.
zeros.
It's 10 to the 100.
Yeah.
Yeah, whatever. Okay. All right. It can't measure that. It can measure millions. Make sense? So this is your bank account, right? And let me know if this is the case, because we could make lunch plans. But let's just say your bank account can only see into the millions, and you got one of these Google dillions or whatever. Your bank accounts would be like, oh well, I can only measure millions. You got so much money, I just read OL. Like it's like that. This can only measure to millions. It can only go as low generally as milli, sometimes micro, but not normally, and it can go as high as millions. So if you have OL, that means you have more than millions of ohms. For our practical understanding, that's a frickin' open. Make sense? If it has more than millions of ohms, that's an open circuit. Cool? Is that fair? You like it? Doesn't matter if you do. Let go of my belt. Second time. OL means to you practically what? Frickin' it's open. It's got so much resistance it can't even read that much resistance. It's open. So if I measure a wire, should it measure OL? Not unless a mouse chewed it or somebody cut it or it's disconnected or something. See how that's the practical. If you measure something and it reads OL, that's an open. On your technician story, you would write it's an open. This is not a short. A short's the opposite way. A short means there's not enough resistance. An open means it's open. So one of the things that we'll clarify going into the part 2 is if you measure a problem in a circuit, you need to be able to use your words. What's wrong? What is wrong? Like when I went into my boss's office, I should have said, what's wrong? Not, I'm going to go back to school to be a mechanical engineer. I want $18 an hour. Pay me, or the toolbox got wheels. I probably would have said it nicer. But guess what? That Pontiac dealer closed 2 years later. Guess who called? No, it wasn't. It was a Chevy dealer actually, but that was the idea. The previous employer called and said, "Hey, you coming home?" And I'm like, "Home?" She's like, "Well, I know you're down at the Pontiac dealer, Wedekind Pontiac, Schenectady, New York. Look it up if you want. I know you're down there at the Pontiac dealer. You know, why'd you lie to me?" And I was sort of like, "I don't know." She's like, "Well, you coming home or not? Because I know that Pontiac just lost their franchise. You're done. You coming back?" And I was like, "Well, it depends on the money." And she's like, "Well, let me look." So I met with her and she looked, she's like, "Oh my gosh, we were paying you $13 an hour?" And I was like, "Yeah, that's kind of why I left." And she's like, "Why didn't you say that?"
Was
like-
this when Pontiac just completely shut down?
Yeah.
08, 09?
Yeah, exactly. The recession was crazy times. And so she came back and the number I got at that time, and I said, "Look, not only they give me 18 when I left, then I got like a couple dollar raise every year and stuff. Now I'm like, I want 25. And she's like, "Yeah, we'll do 25. I'm like, man, I should use my words. I'm just letting you know. I should have really used my words. So as part of coming up in automotive, you got to learn to use your words. So when you have a problem with a circuit, you have to be able to communicate that. So if it's OL, that's open. Make sense? If you have a resistance of 1,000 ohms, does that sound like an open? It's not really an open. That's what's called a high resistance. Make sense? So understanding what this means and being able to use your words is going to explain to other people what you found, right? So if I'm probably past those days mostly where I'm the one doing the work on the car every day fixing them. I get pulled into that still, but mainly what I'm trying to do is have you guys do the work. And then if you come to me and you tell me, well, this is what I got, if you can't tell me you got to open, you got a high resistance, you got a short, like we can't communicate. Make sense? So I'm going to press you on making sure you can use your words and communicate to me, because later you're going to have to communicate that to the customer, to your foreman, to your service manager, to your whoever the heck your boss is, and maybe even like if you're having to work with the factory and troubleshooting and more advanced people and people in corporate or whatever, you got to be able to have the right terminology. You could say, well, I got a reading of OL, and they're going to be like, are you new? And you want to be like, I got open. Yeah, that makes an open is what this means. Cool. I got a high resistance of 1,000 ohms on that wire. Now we're talking. Cool. And that's kind of what it says. For resistance, typically this indicates open circuit because it exceeds the meter's capacity, which is up to millions of ohms, but not higher. Cool? All right, so here you are, you're on auto range. So if I were to cover this up right now, what is that number? We're on ohms right now. What's that number?
1,000.
You have 0.705 ohms, or no, you have 0.705 kilo ohms. So you remember kilo's 1,000, right? So if we were to move it 1, 2, 3, another way to say this would actually be 705 ohms. 705 ohms is the same number as 0.705 kilo ohms. So sometimes the auto ranging can be a little bit of a pain. You know, if for me, I'm just going to move the decimal in my mind. But if this beats you up, you can put it on manual, you can put it on ohms, and it will move this decimal point 3 spots, which will drop the K. Make sense? If I want to drop the K, I need to move 3 spots to the right. It would say 705 and just ohms. Cool? Fair enough? Not that complicated. Then be like, yeah, I have 705 ohms. Cool? So that's how you would proceed on that one. And then to really drive it home, if you were to have 705 ohms, but it were to auto range to kiloohms, you get a 0.705. This is going to be all with the same resistance measured in the circuit. On kiloohms, you get a 0.705. If it were to drop down to 400 ohms range manually, what do you get? OL, it's like out of limits, because OL could be dangerous. If it's OL on auto range, it's an open. But if it's OL on a manual range, all it means is it's out of the limit. And right here, your limit's 400 ohms. So if you have 705 ohms and you only have it manually ranged to 400, it says OL. And you think it's an open, but actually it's 705 ohms. Cool? And these are all manual range. If it goes down to 4 kilo ohms, look what you get, same number. It auto ranged to kiloohms. If you manual range it to kiloohms, you get the same number. Make sense? If you manual range it to 40 kilo ohms, you're going to get a measurement of 0.70. Is this number different from this number? No. We just dropped the 5 at the end because if you're only ranging to 40 kiloohms, it's not going to look 3 digits to the right. It's only going to look 2. And actually, I probably would have thought that would have rounded up. Maybe it would round up. I don't totally know. But either way, you're not as precise. Make sense? What if you were to manual range it to 400 kiloohms? All you get is 0.007. So see how this is less accurate? This was the most accurate you could get. Make sense? So it's a measure of accuracy in a way. If you set it to 4 megohms, it's really looking for megohms. That's going to be even further decimal point to the left. You don't even measure anything because you know where this 7 is now? It's off the edge and it's not looking on the edge. It's not looking that far out. Make sense? So let's say that you guys had 70 cents. That's a quantity of money, right? A little bit. What if I say I'm only looking for dollars? How many dollars do you have? Nothing, so I'm ignoring it. Make sense? You're making the meter not even look for the pennies. You're like, just tell me in dollars. And then over here, like, tell me in hundreds. It's like, yeah, you still got nothing, buddy. 70 cents is $0, and it's also definitely 0 hundreds of dollars. Makes sense? So if it's on 40 mega ohms, you'd be like, there's absolutely nothing, no resistance here. So just understand the auto range, to me, is the go-to, because you don't have to deal with all this. But it could also bite you if you don't notice the little prefix. Cool. Pretty simple, right? And then again, when we connect the leads, remember, put them in the right spots. So like if you're going to do a diode test, you can see the symbol. Look at all those little symbols on there. Okay, now let's say you wanted to do a measurement on a wire that you thought might be, I'll make it really practical. I don't think I've driven my Hummer yet to this class, but maybe last semester. To this one?
Oh, not this class.
But the last one. Okay, that truck is such a piece of crap. It's always breaking on me. I've done so much work, like rebuilt the engine, all that stuff. I custom made headers. I put headers on there. It sounds good. It will break down. It's just the way it is.
It's a GM product.
Knock it off over there, Tony. All right, so its nickname is La Toxica, okay, because it's constantly taking a lot of money, giving me a lot of drama, all the I mean, I put like money like this, like throw it in there. Okay, that truck, everything was cool. The engine's all rebuilt, and then one day I go to start it, and the tachometer starts bouncing and like jumping all over the place and acting crazy, and then finally it sets a code for like crankshaft position sensor performance. Okay, and this goes on for actually, I've been dealing with this for like 6 months. So I check it out, the wires look good, wires test good. As far as I could tell, the wires are good. Put a crankshaft position sensor in it. It lasts 6 months, maybe just a little under. Then it did it again. So I'm like, another sensor? But the first sensor was a Delphi, which is the OEM supplier, but not the GM OEM. So the next sensor I did OEM, boom, and that one lasts 1 month. And then it happened again. And then I'm like, another something else got to be going on here. But each time I'd measure the wire, right? I'd get 12 volts where I'm supposed to, I'd get ground where I'm supposed to, and I'd get good continuity on the signal wire back to the ECM. So the wires are good. Would you agree? I'm testing them and they're good. So I put another sensor in there, and this time the sensor didn't fix it at all. So I'm like, oh, something's weird. Okay, and then I'll be honest with you. On the last time, I'm like, I'm not measuring all these wires again. I know it's a sensor. The sensor keeps failing. So I put the sensor in, it didn't fix it. I take it all back apart, and I realize like, it's gotta be an intermittent in the circuit. Intermittent means sometimes it's good, sometimes it's bad. Would you agree? The first time it was good for 6 months, the second time for 1 month, and then this time for nothing. So I'm like, something's up. I start trying to measure the wires. I measure the wire and it's good. But to be a little more thorough, you know, when the engine's running, stuff's shaking, right? And moving around. So what I actually would do to help myself, I would measure the resistance and then I'd put it on the min-max setting. And then I'd move the harness. I'd wiggle some stuff, I'd shake it, right? So if I'm dealing with an intermittent, this min-max function is like everything to me for this piece of crap truck. That's so rare, but it's also so problematic for me. Let me tell you, I could definitely buy a new one, but I don't know. I kind of want to have the truck that nobody else has, so I deal with a lot of problems, okay? So if I put it on min-max and it says, you know, 0.0 ohms on the wire, but what if I go wiggle the wire and the meter makes a beep and I come back to it and it says OL? What did I just find? It's got to open like kind of intermittently. If I can get it to go from 0.0 to OL when I move this particular spot, you know what that means? Start tearing into that harness, separate it, get it all in there, and I did. What do you think I found? Not exactly, but close. The wire runs right next to the header. Remember the headers? I had to have the headers so I could sound cool and go, vroom, you know, CPM out. Vroom, vroom. Okay, I had factory manifolds on there, had no trouble. Now I put a header on there. It didn't exactly melt it, but where I found that part of the wire, when I would try to move the wire, it was kind of brittle. It was like stiff. So I cut all the insulation off of it, and you could just tell the copper was hard and so it wasn't a full open. It was like a good unless I wiggled it, and then it would be an open, and then it would be good, and then it'd be an open, and the min-max setting totally bailed me out on that. So I actually just finished yesterday replacing all that harness, and I put heat shielding, and I did header wrap, but the min-max setting is what actually got me to diagnose it. So if you're looking for open, and you put on min-max, it'll store the maximum resistance, if we're doing resistance, right? The maximum was OL. Make sense? What about if it was, if we were looking for a short? I was saying an open's lots of ohms, right? But you know what a short is? It's not enough ohms. So if an open would hit the max, it would store the max. What would I put it on to find a short, which is very low? Minimum, exactly. So if the circuit has 4 ohms and I wiggle stuff around and all of a sudden it hits the minimum at 0.0, that's a short right there. So I could use the min function and flex the harness and be like, boom, it hits 0 when I flex it right here. Cool. So you don't want to just rip the whole harness apart and trace each individual wire. There's 2 miles of wire in the average modern vehicle. If that's all you know, you aren't going to fix anything. You got to be able to use the functions of the meter, kind of manipulate it. Ford would actually call that the wiggle test. They'd be like, do the wiggle test. Do the wiggle test. You know, do the wiggle test. Wiggle, wiggle, what? You wiggle the wires. It's saying not you, the wires. You wiggle the wires. Cool. And then, so min-max should be pretty solid. Also, a meter does not, here's what it says, continuously sample the voltage. It checks the voltage at regular intervals. So the reason why you just have to know the limit of what your meter can do. Cool? Your meter is sampling, sampling, sampling. If you have an intermittent issue that happens so fast the meter doesn't catch it, you may not see it on screen. And actually, the min-max function can help to find it, but if it's really something that's extremely quick, you could actually go over to an oscilloscope. So that would be pretty rare, but like if my truck kept giving me trouble, I'd bust out the oscilloscope and I'd graph it, because an oscilloscope graphs voltage over time. So if it had a quick second where it dropped out, the meter would show, 12.6 volts, 12.6, 12.6. An oscilloscope would show a line, then for a quick second it would drop off and come back up, and I'd be like, what the heck is that? Make sense? So the meter's great, but it does have some limits, because remember, it's only sampling at a sample rate. It's not 100% live. Make sense? And so if there's a little bit of something between samples, it won't even know. I have no idea. Cool. And then also you can put hold or auto. If you put hold or auto, it'll hold the value until you turn the meter off. So like if you press hold and then it hits a spike, it'll just display that one on screen. That'll hold that value. Kind of a nice thing. Similar to min-max. Okay, and then again, we talked a lot about these different ports. So this one's the big A, it's fused. This one's the little a, it's fused, but only to 500 milliamps, so that's a half an amp. That's like you'll blow that fuse so fast you don't even know what happened. Cool. COM, what's COM? Common. Yeah, common is generally ground. If you're working on an old tractor, it was actually a positive ground. So it's kind of weird, but generally we're going to say overall that's ground. That'd be like your negative, that's your black lead. And it pretty much stays there. Cool. And then volts, ohms, hertz, capacitor, all that stuff is there. And then remember we talked just a little bit about how we probe. Back probing is something we're going to get into more. When you're learning on the circuit boards, those are very forgiving. They're actually made for bigger probes. That's why we start on the circuit boards. So you learn the measurements. And then once you learn the measurements, you learn to trace the wires and predict voltages. Then once you've done that, you go out onto the car where you can locate connectors and back probe harnesses that are hard to get to and upside down and, Sunny Beach, remember? So, but you got to build up to that. Your first thing is not to go out on the car, because you're going to end up messing some stuff up at this point. Cool. And then also one of the things you'll see, like talking about the leads with the alligator clips. I grabbed an alligator clip, but it looks like I forgot it. An alligator clip can be kind of nice. It'll just, let's say you want to put the negative on the battery. You don't need to hold it there. You can put an alligator clip and it'll hold it, and then you can do your thing with the positive. Cool. Alligator clips? Kind of similar to, I was pretty sure I brought one, but I don't have one. Chuck them. They're mine. Mine now. Okay. Oh, and yours has fuses too. That's nice. All right. So alligator leads. Alligator clips for your leads, I should say. Right. Want to clip this on? Clip it. This is going to hurt. Walk away. I just don't have a lot of feelings, so I kind of feel that. Okay, that's helpful. Very helpful. Keep these with your meter. Cool. All right, and then here's a whole bunch of sample back probes. This right here is something that we're testing this terminal, right? but I'm going to make this as simple as possible. This terminal is a particular size. So let's just say the male terminal is a 1 millimeter male spade. That means the female terminal needs to be probably like a 0.9 millimeters. So that way when the male terminal goes in, it's like a really good solid connection. Would you agree? What if you take your 2 millimeter probe and you ram it in there? Now this is 2 millimeters, and when you connect the original terminal, that's a 1 millimeter male spade. What happens with the 1 millimeter male going into the 2 millimeter female? They don't even touch. They may touch sometimes. They may. So you may like start with this problem, and then a really bad technician will diagnose it, and you'll end up with all these other problems. And you're like, what the heck happened? Oh, it fried these other things. No, it didn't fry anything. They front probed the crap out of all these terminals, and now every terminal they touched is now a bad connection. Make sense? So that's why you got to be really careful about this. Generally, front probing is like scary. It's not to say that once in a while you can't do it, but if I had to front probe something, I'd actually take a little piece of wire, strip the end off of it, take like 1 or 2 strands, twist them together, and I just have like a very gentle little strand that'll make my connection. But what's preferred? Back probing. What's that mean? On the back side, you can actually really carefully go between the seal and the metal terminal and just make sure you get just enough connection. You're not probing where the tension needs to be. You're probing the back, which is a little more, it's just less invasive is what it comes down to. You want to be as least invasive as possible, but it can be a hassle. This would be back probing. So I know that lighting is a little tough, so I'm going to help you. If you look right here, there's a probe going into the back of the connector right there. Boom, that's a back probe. And that would be less invasive, generally acceptable. It does get a little tricky because you need to, that was right. You need to know exactly what terminal it is, but that's part of what we cover soon. Okay, so just making sure everybody knows, even though we're not in the cars yet, that's some of the reason we're talking about it. You could also make your own. A paper clip is typically too big, but a T-pin could be pretty good. You can go buy those at like Walmart. You can buy a big old thing of T-pins. The negative of a T-pin, there's no way to connect it to the lead. But if you have the alligator clip, you can connect the alligator clip here, and then you can connect the T-pin to the alligator clip, and then you have a set. But what's kind of nice if you want to spend the money, this is just like a T-pin, and it connects right to the meter lead, and then it's on. Cool. So we got some options. But again, you still have to be really careful. You gotta be like really gentle with this. And then remember the piercing thing? They have sharp, fine pins and blah, 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 blah. They allow the technician to obtain information. Always re-insulate the hole. How? How you gonna do that? So they're saying, cut the insulation and then re-insulate it. Okay, I guess like maybe some silicone grease. That's not what I would use. They have a thing called liquid electrical tape. It works actually pretty nice. But if somebody works on my car and now they have to dab goop all over the place because they punched a bunch of holes in the insulation, they're fired. Just don't do that. You don't need to do that. If you absolutely need to do that, maybe okay. Okay, like there's nothing technically wrong with this statement, but it's like, don't do this unless you absolutely have to, and most of the time you don't have to. You can back probe at the terminal, at the connector, and you won't hurt anything. And you won't need to like paint the whole car with a bunch of goop. So I'm saying. Okay, so the most common you guys would know. Voltage would be really typical. We might do some ohms, might do some milliamps. We'll get into exactly how we're going to do those here in just one moment. Okay, so let's say here comes voltage. Who can give me a time check?
11:15.
All right, so we're doing okay. I'm sure my battery's good. You're getting ready to do a voltage measurement. You need to prepare by connecting black lead to the common, red to whatever the thing is on your particular meter, probably volt, ohm, or similar. So on this one, I'll start with no leads. Okay, black lead to the common. That was easy. Red lead, then I have to look. Big A? No. Little a? No. V ohm dot, yeah, boom, just like that. And then, well, that's it for now. So we're just connecting them. And then we're gonna select depending on what we want. So if we're trying to measure a battery and using manual ranging, is a battery more than 2 volts?
Yes.
So don't pick 2. Is a battery more than 20 volts?
No.
So that'd be a good one. Why not pick 200? Yeah, exactly. That's when your battery would probably show like a, rather than a 12.6, it just show like a 12. And then you're like, is it 12.0 or 12.9? See, so like if you go too far, it'll cut the decimal point off. Cool. So you want to go as high as you need to, but not higher. So you're still kind of accurate. Or what I would do, auto ranging, put the piece of junk on volts. And then there you go. It'll do a little auto range, but then by the time you actually do the measurement, it should auto range to something that makes a lot of sense. And there's very few exceptions to that. So boom, we just go ahead, put it on volts, manual or auto ranging depending, and then you go ahead and you would place your leads here and here. And again, if you switch them, it's not a real big deal. You're just going to get a negative measurement. It's measuring it backwards. No explosions, nothing real scary. Cool, I think you can do that. All right, so if we were to go over some of the details of how we would measure voltage, now you should know how to use the meter. But when we measure source voltage, that's the source of power in the car. That's your battery. Measuring source voltage is just like this. Boom, just like that. Tell me, what if you were to have it on amps right there? You blow the internal fuse because your electrons would go right through your meter, and your meter in the amps setting has 0 impedance, 0 ohms, so it just poof. Whoops, oh, I had it on the wrong setting. So check your lead. Remember, that was the first step. Make sure it's in the right spot. Cool? Otherwise, you do blow the fuses. So there's your source voltage, but I'll show you another, a couple measurements, and then I want to really make sure you understand these. Available voltage is just what it says. It's measuring how much voltage is available. So if we're functioning on a 12.6 volt system and the positive wire goes over to here, do you see any resistance in this wire? There shouldn't be another load or anything. So how much voltage should be available at this point? 0.6. Exactly. And if you lose like a little 1/10 or so, that could be kind of normal, but it should be 12.6. That's what's available. Here's how you do that. You leave your black lead on the ground. You leave it there the whole time. How are you going to leave it there the whole time? Maybe an alligator clip. Clip it right there, and then you kind of just leave it. And then this one tells you how much voltage is available at that point. So wherever my red lead gives me a voltage measurement that's available. 12.6, 12.6, 12.6. What should come after the switch if the switch is closed? Any idea? Don't overthink it. Should the switch take that much? No. If it's closed, no. If it's a good switch, about 12.6. Let's say we're even down to 12.5. How much should be going into, skip the dimmer. How much should be going into the light bulb? Still 12.6-ish, right? How much should be left over after the light bulb?
0.
Exactly. You just measured available voltage. Available. Now, if it was a test light, it'd be like lit, 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 not lit. Make sense? So a test light can show you kind of like available voltage, but it doesn't give you a number. It just gives you, oh, I think that's about 12 point something. It's glowing fairly normal. If it's dim, it's probably low. If it's really bright, it's like your future. All right, so available voltage. Cool, you got it. The black lead stays here or on any good metal ground, makes sense? And the red lead, you're probing multiple points. You're not poking the wire, but you're back probing or you're whatever. Let's just say if we had 12.6 here and 0.0 here and 0.0 here, 0.0 here, what's wrong?
Blown fuse.
Blown fuse, exactly. Bingo. The available voltage is a great way to do it. So now I want to test you. What was the voltage drop of the fuse? 12.6 to 0, 0, 0. How much did it drop? It dropped 12.6 volts. You know it did, but you measured that with available voltage. So in available voltage, you're seeing what's available. There was 12.6 available, and now there's 0. If there's $12.60 in your bank account, and on lunch you head over to Los Portales and you get the breakfast special with the horchata, now there's only $0 in your account. How much did Los Portales charge you for that breakfast burrito special? 12.6, right? So now there's another way to measure this. This is called voltage drop. And these are like a coin, one side of the coin and the different side of the coin. It's the same coin. So if I did voltage drop, look what I've got right here. This is my red lead, this is my black lead. This isn't measuring available voltage. This is measuring the pressure difference between red and black. Make sense? If we had 12 on available voltage, if we had 12.6 and 0.0, we knew it dropped 12.6. We agreed on that, right? You spent that money at Los Portales. It was probably worth it. But if I were to take the leads and I were to do this, what do you think the meter will read?
Open.
Well, we have it on voltage. So we'll measure open. It should... 12.6 is right. It is right. You know why it's right? Because coming in we had 12.6, right? And going out we had 0. This is measuring the drop. So if you see this measurement, it's measuring the difference between the red and the black. And we knew it had 12.6 and now it has 0.0, right? Well, this is just a different way to do it. Cool? I tend to start people off on available voltage. Put this on the ground, measure here, measure here, measure here, 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 here. Oh yeah, I understand electricity now. Cool? But in practical application, when you're on the car, you got to understand something. Remember how you want your black lead over here? Well, you're going to run around with a 20-foot lead, red lead, you know what I'm saying? So like a lot of times what we'll do is be like, I wonder what the fuse voltage drop is. If I were to do voltage drop, I can keep my leads close like this. And I could do this. And how many volts should I drop across a fuse? Exactly none. You proved that to me when we did this. Available, 12.6, 12.6, 12.6. You drop nothing. You could also do it like this. 0.0, ah, the fuse is good. 0.1, ah, the switch is good. Make sense? If the switch was bad, it'd look like this. 0.0 for the fuse, great. Switch, 12.6. Why is the switch dropping all the voltage? It shouldn't be dropping all the voltage, see? So how you want to do it? Voltage drop is kind of like the T-Rex. You know why? You got short arms. Like that. Either way, how you want to do it, I don't know. You do it either way. Either way is fine. But voltage drop is a very valuable tool when you're on the car. It's kind of big, you know, and you're just, like for example, let's say a headlight bulb didn't work. If I want to test a headlight bulb, I can go do my probes, both of them, right at the headlight. Boom, boom. If it's dropping 12.6 but it's not lit up, that means the bulb is bad. Make sense? Different ways to measure voltage. For now though, we'll probably start with available, cool? But then after you do an available, I'm going to have you do a voltage drop measurement. So you got to be able to do both. Okay, you like it? Doesn't matter if you do or don't. It's too bad. You got to like it. There's your source voltage. I think you can understand that. So if you have a vehicle with issues, you know, you really need to know the source voltage so you can proceed. So if you have a battery that has 12.6, but you have 3.7 available, that tells you there's something wrong. But if you have 3.7 available and you never check the battery, what if the battery's only got 3.7 volts? The problem is the battery, not the wire. Make sense? Or not the switch. So you always start with your source voltage test so that way you have your baseline of what your number should be. All right, so here's again the available voltage. 12.6 is available. Cool. I was trying to remember this. I'm a little bit fuzzy on this one, so I'm gonna say if I have 12.6 here, what should I have right here? And this switch right now is open, okay? What should I have here? What should I have here? You're right, because the switch is open. So the switch should drop the voltage because it's open. It's like a toll road. It's like a bridge. The electrons get to this end and then they're like, oh, the bridge is up. So what do? They just wait. And if you listen very carefully, do you know what they're saying? I'm ready. I'm ready. I'm ready. You got to be real like this, though. You got to get close and you'll hear it. I'm ready. I'm ready. All right, so all this will be 0 volts. Do you agree? Because it dropped all the voltage. Now, what happens, poof, when the switch closes, though? 12 goes through, 12 goes through. Skip the dimmer because the dimmer is, I don't want to talk about the dimmer. Pretend the dimmer's not there. 12.6 to the bulb, right? What about after? 0. So the way I visualize that, you got a bunch of cars. They're all waiting at the toll bridge. No cars make it through because the bridge is up. The second the bridge drops, all these cars, but guess what? Right here, there's an accident. The load is always like a traffic jam. It's a delay. Now there was an accident here before, but you know why it didn't matter? Because the bridge was up. So nobody was fighting each other because the bridge was up. Then once the bridge is closed, all the cars are going to rush down to here, 12.6 volts, and then they're going to be kind of like stuck. There's not going to be a whole lot flowing through right there. Make sense? So that's how I kind of visualize what the voltage will be. The voltage will go as far as it can, and the load will always consume it proportional to the amount of resistance it has. If all this is closed and everything is good, this is the only load, you'll drop the full 12.6 right there. In reality, let's say this switch has a tiny bit of corrosion and maybe you have a little bit of a connection at the male-female terminal. Let's say you start with 12.62. By the time you're through the fuse, you're at 12.60. By the time you're through the switch, you're at 12.5. Then this lamp will drop to 12.5. That's still going to be just fine. It's going to be great. If your switch were to drop 4 volts, though, now your light's only getting access to 8 volts, 8.62. That bulb is going to be dim. Cool. How would you measure that? 12.6, 12.6, 12.6, 12.6, 8.6. If I went from 12.6 to 8.6, what did I drop right there? 12.6 to 8.6. 4 volts, right? Should I drop 4 volts across the switch? No. Because if I drop 4 volts here, that only leaves 8.6 for the bulb. That bulb's going to be dim. So we can do all our diagnosis with the voltage, available voltage too. Cool? Okay, or like in this case, in fact, we'll take voltage drop, but I think it's actually more simple here. Remember how this switch just dropped 4 volts with the available? We had 12.6, 12.6, 12.6, 8.6. I could have also done available voltage like this, and what would I have got on my meter? What would my meter show? It wouldn't be 12. What am I dropping? 4. It would read 4.0 volts on the meter, and you'd be like, whoa, I'm dropping 4 volts across the switch. See, and then you would have your short arms, and you could be like, I dropped 4 volts across the switch. That's not right. Make sense? If you want, stretch them all out and poke and poke and poke. That's fine. But like 4 volts, that switch is no good. I already know it. Makes sense without stretching myself out. Okay, you like it, you love it. Then there's the voltage drop again, showing like you can measure the voltage drop of this light. You could measure the voltage drop of this switch. You could measure the voltage drop of you can measure the voltage drop of the wire too. Measure the voltage drop of the wire. How many volts should the wire drop? Pretty much nothing. Yeah, nothing. About nothing. Nothing-ish. Okay.
How many volts switch drop?
It depends. Sometimes they'll say something different. A lot of times the number I hear is potentially up to a half a volt. Yeah, 0.5, 0.5. 0.1 would be good. 0.5 would be probably still okay. You know, and they might have a specific spec depending on the exact switch. But if it's under half a volt, I'm probably not really sweating it. Okay, now take a look at this. This is going to be a bunch of available voltage checks, okay? So I want you to think about these in your mind. In fact, we'll even go like this. All right, let's talk it through, and then let's see if we're accurate. So this is going to be like this is going to be an exercise right now. Here's my red, here's my black. What do you think I'm going to get here if the battery's fully charged?
12.
Do we agree?
Yeah.
I agree with you. I'll go with that. What do you think I'm going to get? Let's say this switch is open. What am I going to get? You see this right here? With the switch open. You think I'm going to drop no voltage across the switch if the switch is open?
4, right? Okay.
It's going to be more than 4.
No, 12.
All of it. It should drop all of it because it's open. It's a full-on open circuit. If it's open, the voltage drop. Remember, the cars are here, and then they're like, oh, how many make it through? Nothing, because it's a full open. No cars make it. So I would, if it's open, let's make a note. If it's open, I think we'll drop 12.6. But what if it's closed? More or less nothing. That's what we were saying. Maybe 0.1. As long as it's under half a volt, I'm not really tripping. So if it was closed, we should drop kind of nothing-ish. Let's give it a hard number, though. Yeah, 0.2, something like that. That'd be cool. All right. Now, this is a little different. So this one I'm going to struggle with. So I'll tell you what I'm actually going to do to change it to make it more simple, because I could do simple math. Let's just say the battery was only 12.0. If the switch was open, it would drop 12.0, right? The full source voltage. Now, when we get to this resistor, we got an issue, because look, this one's 4 ohms. And this one's 2 ohms. So you remember I gave you all those lessons about the siblings? So if parents pass down $12 and this sibling is twice as powerful, and this one's half as powerful, they're going to split that money up in proportion. This one gets double and this one gets half. So what do you think those numbers are if it's 12?
4 and 8.
4 and 8 would do it. See how Ronnie figured that one out? If you look at it's going to be 12. If this one took 8, this one took 4, is 8 plus 4 equal to 12? Yeah. It always has to, it's $12. It's getting spent. It's always going to equal the source. Cool? So the way you figured that out is you paid some pretty good attention in Ohm's law, but we mostly substituted the numbers in. Remember, the math is, I could do math, but it's not something we commonly do on the car, so you'll see I'm a little bit rusty. So if I were to just kind of like punch some numbers in and see if they make sense, yeah, this one has to be double and this one has to be half and it has to equal 12. That's how you figure it out. So let's just say I put the meter like this. How many volts are we expecting to drop? You already know this answer. It should drop 8 volts. So V3 should be 8. V4 should be 4. Cool. And this, by the way, for extra practice, they do have some of these in your book for you, so you can do more above and beyond what we're going to do. Now let's see how we did. You know what? I forgot to put the answer key in there. Might be. The good news for you, I know the answers, and your answers are all correct. The answer key was in the book, though. All right, we're going to do a couple of those together. This one, we did this one together, so I kind of jumped the gun. But that one, if you understood what voltage drop should be at each of those points, you're in really good shape. Like, very good. If you didn't, it's okay. We're still doing them. And then just remember, when we talk about the volts, you might have to auto range it. So let's say we do a little bit of this practice. This is the practice I thought. All right. I have 3,000. Can you see these numbers? We'll do them one at a time. I have millivolts, 3,233. 3,233 millivolts. Equals how many volts? Don't yell it. Let's think about it for a moment. How many volts is 3,233 millivolts? Let me think. Millivolts are over here. So I'd go all 1, all 2, a 3. See, 3 spots. The decimal point's here, right?
3.233.
3.233 volts. Did I get that right? 3.233. That's it. You did it right there. 3.233 volts. You did it. Okay. All right. Now I've got 50 millivolts equals how many volts? So here we go with a 50. 50 millivolts. I'll put a 0, a point and a 0 just so you can. And we're again going to volts. So isn't it 3?
0.050. Yeah.
Woo, 0.050. You guys have got this. And it's up to you if you want to put the 0 there. That probably makes sense. All right, now this is different. 9.48 volts to millivolts. So now the 9.48 is here.
9,480.
Whoa, too fast. Here we go. Now we're moving the decimal the other way 3 times. Make sense? Because we're going from volts to millivolts. So, how many times?
3.
So then this becomes the 0. And this is the point. So it's going to be a 9,480 millivolts. Everybody agree? You could do that. Okay, one more.
270.
Oh my goodness, see, you're getting so fast, you already know. 270. See, it's not really all that hard. Huh? Think you can do that? I think you can do it. If you can't, if you do a little bit more practice, I think you'll make sense. Okay, here it goes. Gone. Okay, more with measuring. Okay, so I think we mostly, you know how we did that last one and we talked about available voltage and voltage drop? Now I want to explain it to you. The voltage drop is the potential difference between 2 points. The sum of all the voltage drop in a series circuit equals what? What's the sum? It always has to equal it. What's the sum of all the voltage drop equal? What was the supply voltage? That's like the battery, right? Exactly. So if it's a 12.6 volt battery, all the voltage drops will always equal 12.6. Cool? It has to. Now there's a reason why that's important. And for now, we'll just briefly cover if it's a parallel circuit, each load should get access to the full voltage, right? So each load should drop the source. But on a series, all the voltage drops should equal 12.6. Unwanted voltage drops becomes a problem if it becomes excessive. And occurs in parts of the circuit other than the load. What's the load? Maybe bag it up for you. What's the load in this point? Exactly. So we're expecting to drop 12.6 volts here. What if we have voltage drop in other spots? That load doesn't get all the voltage it's supposed to get, which means it doesn't do the work it's supposed to do. Is that fair? That's the reason that we're very concerned about measuring voltage drop. So like if you have a good circuit, the resistance and everything is good, it should be very low resistance, causing a small and insignificant voltage drop. And that should leave pretty much all the source voltage for the load. Cool, and then the bulb's gonna be bright. What if it's a motor? If the motor gets all the source voltage and consumes all the voltage drop, what's the motor gonna do? Electric motor. It's not gonna be a bright bulb because it's not a bulb, right? It's gonna be like a strong, fast moving, good moving motor. But if you have excessive voltage drop, the light bulb's dim, right? If you have excessive voltage drop, what's the motor? Slow, weak, yeah. You try to put your window up and the window goes, like that. Make sense? We'd have to troubleshoot it just like this. Cool? An excessive voltage drop in the circuit cables, connectors, and switches reduce the efficiency of the circuit. So like with my truck, I was measuring resistance. I could have done that as a voltage drop measurement. Actually, the problem with it, if you want to measure voltage, voltage drop, the circuit needs to be active, needs to be working. If you want to measure voltage drop of headlights, headlights need to be on. That's hard to do on a sensor when the truck won't really run. And so measuring resistance is a good way to do it kind of like dead. So if you want to measure a wire resistance, measure it resistance. But if you can measure voltage drop, actually it's more accurate. Resistance is just going to strain it with the 9-volt battery. It's kind of a basic measurement. If you can measure it with it active and working, the voltage drop is going to tell you like much more information. It's a dynamic test, you could say. All right, so here like we're just going to do some basic tests like this. If you look, this is the load, and the load is dropping 2.941 volts. That doesn't, if this is the only load in the circuit, that's too low. If it's a 12.6 volt circuit, right? So is this a good measurement or a bad measurement? Would seem bad, but what was the source voltage? I don't know. I see a couple AA batteries, so actually that might be fine. But the point is, if you measure the source voltage, that whole source voltage should be dropped across the load. Cool? Again, over and over you're going to hear it. And if it's dropping less than that, that means it's because it's sharing it with something else. And that's, remember, unwanted voltage drop is a problem. That would be unwanted. I mean, we need to find where the voltage is dropping where it's not supposed to be dropping. Cool? And it does talk about, specs. So remember I was saying maybe up to 0.5 volt on the switch. Overall, the unwanted voltage drop should not exceed 0.5 volt. If it's exceeding 0.5 volt, that's a problem. If it's a 24 volt system though, it could be up to 1 volt and still be considered a healthy circuit. Cool, like say it's an individual wire or a connection, we generally don't want 0.2 volts. So I think even 0.5 volt for a switch was probably pretty generous. 0.2 volts would be a little more like holding it to the real standard. You shouldn't drop 0.2 on a connection. You shouldn't drop more than 0.2 on a wire. You shouldn't drop more than 0.2 really on any individual component. Only maybe kind of exception is sometimes a switch, but this is pretty good even for a switch. All right. Okay. So here we have got the meter set up, and that's kind of what it's saying. And then from there, let's say, whoops, it's locked up on me. Huh? Why do you hate me? That's weird. Let me restart PowerPoint. Let me try to restart PowerPoint. Huh.
Did the internet just crash?
I don't think so, because I have the file downloaded. Arleth, you pause me and we'll... All right, so once we're done with this is what you're going to build, okay? But for some reason, I can't get to show on full screen. So let's just run through it. All right, you guys in the back row. If we build it like this, the positive will be on the top. We'll have it go through a fuse. We'll have it go to a switch. We'll have it go from a switch to a load and to ground. That's as simple as the circuit as we're going to start with when you actually build it. When you build this circuit, you're going to do the measurement of each of the points, okay? So that's what we're going to do. You're going to actually just measure the voltage. You can measure it in a couple different ways, but that worksheet I gave you shows you to build the circuit. And then on the next page, it's going to ask you to do measurements at each of the points. So like, for example, number 4, measure the source voltage. You can do that. So this is what we're going to do. I'm prepping you on it. Predict the voltage is the bottom half of 4. So before you measure it, you're going to predict it, okay? So we're gonna skip this diagram, and I'm gonna walk you through how to do the predict on another one, okay? And it's gonna be this one. So we'll do this one together. How would you begin with measure the source voltage? Meter lead in the V, turn it to DC volts, right? And then we're going to take our meter and we're literally just going to go to the battery. Bingo, just like that. And let's just say it gave us 12 volts. You're going to end up, you're going to predict about 12 volts, right? And you're probably hopefully going to get about 12 volts. Now, I think it may be easier for you to see if I just use the Sharpies, but so now I'll become the meter. My arms will become the leads, right? So if I asked you to predict V1, isn't V1 the source voltage?
Yes.
And you expect, and then this gives you the explanation. V1 equals 12 volts. V1 has measured the voltage directly across the battery, so the reading should be battery voltage. Cool? All right, now what about V2? Think about V2. Depends on the switch position, doesn't it? Right, so in this stage of your training, you're working to understand and predict. Cool? I know you could measure this, and you're going to get really excited when you get the meter, and it's great that you can measure, but you need to be able to predict a good measurement. You need to be able to understand, like, hey, this is good, or hey, like, hold up, something's wrong. Cool? So some of this works with your mind, not just with measure, and fill out a bunch of crap. If I wanted you to do 1, 2, 3, 4 measurements, it would take you 1, 2, 3, 4 minutes. You'd have the answer on the paper, and we'd move on. What would you have gained? Thank you. So we go about like this, right? Prediction. So V2, I agree. It should drop 12.6 if the switch is open. Why is that? Because the switch being open, the cars, right, the electrons should go right to the edge, and they should, what do they say if you listen?
They're ready.
I'm ready. Just like that. Okay, that's how you know. And there you go. You have 12. In this case, we got 12 volts, right? A 12 volt drop, boom. That would be a good measurement on an open switch. But what if the switch was closed? Ish, yeah, 0. You should get really no more than 0.2. Sometimes if you're generous, maybe a little bit more, but 0.2 would be good. So if the switch is open, it should drop everything. But if the switch is closed, it should drop just about nothing. So you should be able to predict that. And then, by the way, when you go to test it, I want you to test it with the understanding like, oh, with it open, I think it drops 12. And then with it closed, I think it drops maybe about 0.1 or 0.2. And then see if the electricity does what you thought it was going to do. And then if it does what you thought, that means you understand it well. And if it doesn't, that means you don't quite understand it, or maybe there's a bad component, and that's very possible in these kits. So we might do some troubleshooting, okay? Now, this resistor number 1 is 4 ohms. We're going to voltage drop that one. And if there was only one resistor, okay, let me modify this. If there was only one resistor, like how we're going to do it in the activity, how much should it drop on if it was only one resistor? It should drop the whole 12, exactly. Minus anything that you might have lost in the switch, which should be minimal, cool? So if you predicted if there's one resistor and it should drop 12 and it drops 6, something's wrong there, and you're like, do I not understand this? Or maybe there's another fault in the system, right? So it's a big thinking game at this point. But now we covered this one once before. Remember I told you I had the answer key, but I jumped the gun a bit. I was just trying to show you the circuit before. Ronnie figured this out. If this has 4 ohms and this has 2, now we're back to having the 2 loads in series. How much should this drop and how much should this drop? So this should drop 8, I agree. And this will check out, V3. With the switch open, it should drop 0. But if the switch is closed, it should drop 8. And then this one should drop 4 with the switches closed. So those predictions were accurate. So I want you to take the time, consider the predictions, write the predictions out, and then you're going to actually do the measurements and see if they match. Now let's go about this one more way. What if I were to say available voltage? Plug your black lead on the ground and measure here. What do you expect? 12. How about here?
12.
How about here? If the switch is open, I agree. What if I were to close it? What should you get? About 12. Maybe by now you're at 11.9. Because you can lose a tiny little bit along the way. Cool?
Why? 'Cause it was open.
If it was open, it should drop all 12. But even if it's closed, consider a switch, if you remember from components, has those actual contactors, right? those contactors, if they're perfectly clean and pressed together pretty hard, you might drop nothing. But remember, they're kind of like springy and they're held, and you might not have a perfect connection. And if you have just a little bit of resistance right there, it'll drop a little voltage. It'd be acceptable to drop 0.2 volts. That'd be still a good switch. If you drop 2 volts or 6 volts, you'd be like, oh, that switch has excessive resistance. I know, because it's dropping excessive voltage right there. It shouldn't be dropping. Remember, like this is the allowance, $12. This child's expecting to get $8. This child's expecting to get $4. We didn't make no allowance for the switch to take 2 volts. If the switch takes 10 cents or something, cool. But if the switch be taking dollars, we got an issue here. Now this child's only getting $7 and this one's getting $3 because the switch took 2. We'd have to repair that switch. Make sense? That's what we think about it. So prediction should work just like that. You should know what you're going to get at each of the points. Cool. And now with the switch closed, this was the difference that I missed. If I had this right here, what do you think? 12. What do you think about right here now with the switch closed? With the switch closed?
0.
Okay, let's see if that's right. It should be about 0 volts. It could be 0.1, 0.2, that'd be fine. Okay, whoops, I went a little too far. Okay, now with the switch closed, summarizing, you told me this once, how much? And this one? And so we can compare that to the answer key. Should be an 8 volt drop. Should be a 4 volt drop. And you could actually do the Ohm's law to calculate that the long way, but because they happen to be 4 ohms and 2 ohms, you knew that one was going to be double, one was going to be half. So it's an easy way to do with no math required. Cool. And so I'm walking you through this, but if you're not getting it and you need more and more practice, there's quite a bit of these in the book. And then also when we do this, there's going to be pretty good explanations for why you're getting the numbers you're getting. So a realistic good goal for today would be to be able to measure voltage and predict voltage. And you'll see, I'll skim like some of the next stuff we're going to do was going to be measuring current and stuff. You know what? I think just doing voltage today would be a good goal. So I think we're just gonna focus on that, which means I'm gonna insert and make this the part 1, and then we'll spend some time doing the predictions, doing the measurements. Iron sharpens iron each other. If you don't understand it, explain a little better. If anybody wants the real answers, ask Tim. He's got it more thorough than me. And so we'll, but the only problem is if you're his partner, you ain't gonna do anything. He's gonna have it done already. Matter of fact, that sheet's probably already done, and I didn't even get you anything. Boom, boom, boom. But that's what we're gonna do is really working on this. So voltage for today. You guys cool with voltage for today? And that means for next week, we'll get into measuring. I think we could do amperage and resistance in one day, but we spent a lot on the meter, so that sucked up a lot of time. All right, now let's walk through this one to see if you're picking up what I'm saying, because this one's actually got a defect. Source voltage, what do you expect? About 12. There you go. Voltage drop across the switch, what do you expect? Okay, so far you're good. Voltage drop across V3 is a bulb. So V3, it would depend on the exact resistance, but this is the lesson. If V3 was a good bulb, but we unintentionally had unwanted problematic resistance on the ground, do you understand what would happen to the voltage drop right here? We're expecting 12 on 3, right?
Yes.
But what if we were dropping 2 down here that's not supposed to be there? Somebody's pulling $2 of allowance money with no permission, so how much does V3 get? It was supposed to get 12, but it's only got 10, huh? So the bulb's going to be a little dim. Cool? So then you'd be like, wait a minute, this voltage drop is only 10 volts. That means there's a voltage drop somewhere else. And in this example, we drew it in here. there's resistance on the ground circuit. And so you'd have to measure that with your meter. Sometimes you can see resistance. It looks like a wire that's cut and it's green and corroded inside. But sometimes, like in the case of my Hummer that I told you about, there's resistance in those wires, but I couldn't see it. I couldn't see anything. I had to measure it. I had to put it on resistance. I had to put it on the little min-max and wiggle some stuff. And then I could measure the resistance, but I couldn't really see it. You see what I'm saying? So part of this exercise is going to be, do you understand if there's unwanted resistance, what that causes? Unwanted resistance means there's going to be a voltage drop that's unexpected. We might expect to drop 0.2 volts across the switch, but we are not expected to drop 2 full volts across the ground. That's just a wire. We shouldn't be dropping 2 volts there. That's the reason we're only getting 10 here. That's the reason that bulb's a little dim. Make sense? So walking through, doing the predictions, and then if you measure 10 volts, you'd be like, well, where am I dropping it? So I'll show you 2 ways to find that drop. We'll do available voltage first because I like that. All right, you bottle boys over there, why don't you set the bottle down and chill? Here we go, available. This stays on the ground, cool? What's my reading? What's my reading?
12.
What's my reading? 12-ish still. It's closed, so it shouldn't be 0. What's my reading going into the bulb?
10,
It should be 12.
but it's 10.
Well, in this case, it's not. Going in is still 12. Ready? Because this is available. We didn't measure the voltage drop. We're doing available. If I have 12 here, but I have 2 coming out, now what did it drop?
10.
Exactly. See what I'm saying? So the available voltage method, you're basically saying, I started with 12, I still have 12, I still have 12, I still have 12. I dropped, but I have 2 left over. The load should have consumed the full 12. Why do I have 2 left over? If I have 2 left over on the ground side, I can already tell you the resistance is on the ground. So I'd go like this, 2 volts, 0 volts. So I'm dropping 2 volts on this ground by checking available voltage. That would be that's a fail. That's a problem. Make sense? Now let me show you the other way. And I want you to test it both ways on the board. Voltage drop, ready? This is kind of the same, cool? 12. And then I move both of them up here. How much should I drop here?
Nothing.
0. How much should I drop here? How much should I drop here? 12. But let's say I drop 10. Can you see how you're like, wait a minute, this bulb only dropped 10 volts. You already know there's resistance down here, but how do you find it? Like this. How much am I dropping here in this case? 2 volts, and I shouldn't be dropping 2. You should never be dropping 2 volts on the ground. Make sense? 2 different ways. The head side of the coin, the tail side of the coin. It's the same voltage drop and available voltage are just different ways to measure the same things. Cool? So I want you to be able to measure both. You want to do it one more time?
Yeah.
Okay, one more time. Available voltage, I slam the ground right there on the alligator clip. I leave it, I don't touch it again. And then from there forward, everything in the red lead is my test. 12 volts. 12 volts going into the switch, right? How much should I have coming out?
12.
About 12. How much should I have going into the bulb? 12, because nothing's consumed it yet. Coming out of the bulb, I should drop the full 12. We agree? But I didn't. I only dropped 10, and I know that because I got 12, and now I have 2. I still have 2 volts available after the load. That's something ain't right. Make sense? Then down here, I'm to 0. So if I'm going from 2 volts to 0 volts, I have a 2 volt drop on the ground. That's a fail. Cool? Voltage drop. Here we go. 12. How much?
12. 0.
0. Yeah. How much?
0.
How much should it be?
12.
12. But let's say it's 10. How much is going to be here?
2.
You know it's going to be 2 because in a series circuit, it always drops the full source. You're just finding out where it drops it. It should have dropped it here, but instead it dropped 10 and kept 2 for here. That would be a fail. 2 different ways to diagnose the same issue. You like it? You think you can do predictions now? Cool. So that's kind of what it's saying. Right? Like this. I mean, this is basically a similar one, but I'd like to point out 3 ohms and 3 ohms. So are these equal? Now think about what that could mean. If this is a 3 ohm and this is a 3 ohm, this is like the kids are twins. They're equal size and weight, which means they're going to split the cash. Would you say?
Yes.
All right, here we go. Available. Tack it on here. What do I have? I agree, it says that. Okay, this switch is open. What do I have here?
0.
12 going in. See, I'm before the switch. 12 makes it to here. 12 makes it precisely to here. So if I probe here, that's 12. What if I probe here?
0.
And 0, 0, 0, 0, 0, 0, 0. That's available. Because it's open. Voltage drop, ready? T-Rex arms. Wait, let me come back to it because we ain't on that worksheet yet. I'm showing you, preparing you for the worksheet, so you don't need me. Here we go. 12, you agree?
Yes.
Ah!
0.
You don't have an agreement. 12 because it's an open, huh? That's correct. Look at this. It's an open circuit. It should drop 12 volts because it's open. You get me? Dang it. So actually, this would be a whole waste of a test. Honestly, if you want to test this, close the switch. Remember, because we want to test the circuit while it's trying to work. If you want to test the circuit while it's off, what kind of test is that? Now we close the circuit. Okay, ready? Available. 12.
12.
Coming in?
12.
Going out?
12.
I agree. Going into the first one? Coming out of the first one? 6 is correct. How'd you come up with that? Half. Because you can see there's 3 ohms and 3 ohms. So this one's going to take half. This one's going to take half. But both of those should equal this. So if you had 12, what's half of 12 is 6. Cool. So 6 coming in, 12 going in, 6 coming out, which means how much is available at the beginning here?
6.
And how much is available here?
0.
Should be, exactly. Okay, now voltage drop. 12. What we got?
0.
0.
Definitely 0. It should never drop the voltage across the switch. It should drop across the load. Here? And here?
6.
Exactly. Nope, this should drop 6 because it's the bulb, and this should drop 6 because it's the bulb. There are 2 loads on the series. Okay, bingo. Yeah, then I got you. So you're 1 ahead of me. It should be 0. Now, the thing is, though, if we dropped 6 and 6, we already know this is 0 because there's already equal 12. But yeah, you could do one final one in there, just because. Now, what if it was like this? Ready? 12, 0, 4, 4.
There's another load waiting.
Exactly. So if this only took $4 and this only took $4, someone else would be taking $4 of those that allowance money, right? 4 plus 4 is 8. If we had 12 and this took 4 and took 4, where's the other 4? Maybe it's here. Or what if I skipped the switch and I went 8, 8, and I measured this and it was 0. Then I came back up here and I measured 4. I could be losing 4 volts dropping across the switch. What part needs to be replaced? Bingo. You just did a diagnosis. Congratulations. You are special. And here's all the cheat sheets that we already talked about. Cool. And then on equal loads, we kind of already covered. So I think you're probably pretty good. I think the next step is going to be, I can't get my computer to show up full screen, but your next step, we're going to build out this. So let's go ahead and do that. But first, we'll pause. Not stop, but pause. All right, here's the experiment. So we built the circuit, would you say?
Yes.
So we've got, this is the source, right? Coming top down. Source goes through a wire. Source, good. Through the wire.
The fuse.
Through the fuse. Here's the fuse. Through the switch. Here's the switch. Good. Through the switch over a wire. Here's the wire. Through the bulb. There's the bulb. Bulb to ground. Okay, so this is your wiring diagram. You built it. Cool. Very nice. Does it work?
Yes.
Boom. So we got it. All right. Next step in really trying to understand it, we need to measure the source voltage. Show me that. .0204, right around there. I agree. Next, we're going to do predicting the available voltage. All right. So that means we won't need the meter. We'll turn it off. And you just use your meter and pretend you're going to measure the available voltage at point A right here. You see that, right? Use your meter and pretend you're going to show me so I can see it. See point A? It's going into the fuse, right? How would you do that?
So you test it like from there you'd be able to see your available voltage. Might
Good.
be backwards.
But yeah, exactly.
Yeah.
So what you're doing is good, but backwards.
My bad.
Close.
Test the point. Oh wait.
He's got it.
Oh, you did?
All right. I want to break it down for you. The ground, we're going to leave on the ground, and that's the negative terminal. And then this one tells you what's available, and you want to know what's available going into the fuse, so I agree. The other way you could do it is you could put this one down here on the frame, so this is like the chassis ground, either of these spots, right? And sometimes I just do that so the wires aren't all crossed. So that would be available voltage. Now, we're not measuring it, we're going to just talk it through. If this is 12.2, it went across the wire. What do you expect to be at A? 12.2. Then it's going to go through the switch, and then B, test point B is coming out of the switch. What do you expect right here?
So it'd go through the fuse first.
Oh, sorry, you're right. Fuse. So it'd be fuse. This would be test point B. What do you expect through the fuse?
12.2.
About, and is it possible it might drop a little tiny bit?
Yeah. Yes.
Maybe, but
More like
you know, but maybe 0.1 or less. Cool. So that would be B. So I would agree we should have about 12 volts. Then it's going to go, the fuse shouldn't drop much. Then it's going to go through the switch, and this is test point C. What do you expect to be available?
about 12.2 still.
I would say so. Maybe a little tiny bit less. Then it goes across a wire to test point. That went through the switch. So C is going into the switch, D is coming out. So if C is going into the switch, D is coming out, that should drop just about nothing, right?
Yeah.
Then, and sometimes, by the way, the switch can be the most problematic. Like that might drop 0.1, 0.2, that'd be good. If it's dropping 1.0, that'd be bad. I agree. So it should still have 12 volts going, 12.2 here, mostly 12.2 here, maybe 12.1. Going across the wire, what do you think it should drop? Or what do you think the available voltage should be down here?
It should still be
Yeah.
about 12.2.
Yeah, it should still be about 12.2. So I would agree we should maintain the 12.2, the 12.2, the 12.2. If it's closed and good, still pretty close to 12.2. Across this wire should still be 12.2. I agree. Then we run into something. Test point F is the first one after the load. Would you agree? So that would be 12.2 here. What do you expect to be after the load going to ground?
0.
Around 0. So that's what I would say as well. And that's what your numbers show. Then the next step was to actually measure it. So I'm gonna hold this. I want you to give me available voltage at point A, which was going into the fuse. Remember that? Yeah. Either one of you. Okay, 12. You know what we were saying? 12.2, 12.4, right around there. Cool? Yeah. All right, what about after the fuse? 12.4, we didn't drop anything. So is that fuse good?
Yeah.
Heck yeah. All right, how about through the switch? Huh, why is that?
It's because it's open.
It is. So we went from 12 to 0 because it's off. Flip it on. Bingo. We got 12.02 2 or 3. So we did drop 0.01-ish, 0.2. That's normal. Okay. Then we want another test coming out of that wire. And we drop nothing across the wire. That's perfect. Now, what about measured after the bulb? What do you expect again? 0. What do we get? About, now, is that 2.5 volts?
No.
Now, check this out. This is part of the lesson. That's 2.4 millivolts. So that's actually 0.002. Yeah, so that's basically 0.
Yeah.
See how the auto range could trick you a bit. Cool. And then go ahead and give me one more available voltage right at the ground, just because that should be a full 0.00000. So you can see it. It does change just very slightly. All right, so that was available voltage prediction and the actual. Nice job. But your next step is voltage drops. So you just sample what a voltage drop would be for me. Yeah? You tell me. Okay, so what are we voltage dropping right here? We're measuring exactly the wire. So we're measuring between the positive battery and just the wire. So this is saying point A to B. Now, if we were to look at that picture one more time, A to B would be basically the power. Oh, it's actually the fuse. So I had that wrong. So right now we're doing really the battery to A. That first box is supposed to be A to B. So we'd be voltage dropping the fuse. So show me just the fuse. What would we expect drop across the fuse?
About 0.
Pretty much 0.
Yeah.
And we know 0 actually because you already could have calculated the voltage drop by doing the available voltage. Remember, we had 12.4 and then we had 12.4, so we already know.
Yep.
So that'd be predicted. Okay, what do you predict across? We won't even do it like this. What do you predict across the switch? What's your voltage drop across the switch?
About 0.
About 0, but you notice it might have dropped like a 0.02.
Yeah.
So yeah, about 0, but maybe a 0.02. Across the wire, about 0. Across the bulb, huh? Full source, yeah. So the lesson is, it should drop the full source voltage at the load. If it's dropping less than that here, you know you got unwanted voltage drop somewhere. So right across the load, we should drop the full source. You remember what the source was? 12.04, I think. Yeah, so it should drop 12.04 in theory, but if we drop 0.02 here, it might only drop 12.0 here. Yeah, or so, yeah. And then we should drop 0 here. So now you go ahead and measure voltage drops. Is in there. Okay, so your voltage dropping the wire, and you're getting 2.4 volts. No, that's millivolts. So 0.002, yeah, so that's about 0. Drop in the fuse. You're actually getting slightly more. 0.0, you're really low. 0.004 millivolts, so that's almost nothing. Okay, switch. Again, 2 millivolts, so that's 0.002. Actually, that's not even, yeah. If this were volts, that'd be 0.0019. So 1/2 of a volt, that's normal. Remember, that's about the limit, though. That is the limit, but that's normal. All right, what about that next wire? About 0-ish. About 0, yes. And then the bulb. You're dropping the 12.02. Good. And then the ground. All right, so that's good. Now the only thing that could have made this a little bit more clear is if we were to do it on auto range. Go ahead and give me the switch voltage drop again. Yeah, switch. All right, see, I manually ranged this to just volts. So now you can tell it. That's basically 0.
Yeah.
So sometimes manual ranging this could be helpful. Now go ahead and give me the wire right here. And you'd expect it to be 0.001 or so. There you go. Just about nothing. Go ahead and give me the bulb. That's gonna be about 12.02. Oh, but see, the auto ranging helps us to not get this. So I have it on the wrong range, 12.02, right? So now I think I just put it back on auto range.
Right here, we have to do this.
Cool, so you did good. All right, there we go. All right, so did all these work? Yes. Now somebody has a defective one, so that's gonna be my next visit. But good job. All right, different meter, but that's okay. So here, you got 12.02 for source. I'm gonna stand right here and we'll watch you.
So going in, there should be 12.
12 available. 0 coming out of the fuse. Hang on, let me get a good view of that. Pull that meter off there. So you had 12 available and you dropped to 0 available. So you basically, if you were to reword this, you have power coming in but no power coming out. That's a clue. Now if you started with 12 and you ended with 0, what do you think your voltage drop is?
The fuse.
No, what do you think the number is? Show me the voltage drop from here to here.
So, what voltage drop?
Yeah, voltage drop. I'm not showing a 0. Interesting. You're showing a 0 voltage drop. That part doesn't make a lot of sense. Show me the available voltage one more time. 12 in, show me out. 0 out. All right, show me voltage drop one more time because it's got to be dropping it.
0.
Well, let me keep it right there. Let me retry that. Try it again. Huh. All right. Remember what my foreman told me?
You need a multimeter.
Let's try another meter because something's weird here. The homie's got a fluke. Get this fluke meter on that job. All right, so you got your meter to read 12 volt voltage drop, so you're good. Now I don't know what you did. You wiggled it or what?
No.
Oh, you have to test it live. Oh, you have a very interesting thing.
Yeah.
Show me this on the fluke just for reference.
Okay.
So there I was making fun of your meter, and it turns out it's actually a really unique, different issue. So you got a voltage drop. Oh, that's available. Okay, yeah. Show me the voltage drop across the fuse. Okay, so your voltage drop across the fuse is good, but when you actually test it live, did that work?
Yeah.
Okay, you have 12 volt drop with it live. You have a no volt drop with it dead. Does that make no sense? It doesn't, but I'll explain it to you. But what I'm gonna do to explain it, pull that fuse and actually pull that fuse, give it to me, put a new fuse in and we'll verify it's fixed. Well, first off, now you know it's fixed. But let's go ahead and we'll do that same voltage drop. So you got almost no voltage drop, on, off, or whatever. That's a good fuse. This is a bad fuse. Now I'm gonna sneak in a quiet place and explain why. All right, let me explain what we got here. So this is the fuse, all right? And if you look in the light, the fuse seems okay. But we proved otherwise, remember? So here's the breakdown. When the fuse is in and you have the switch off, there's no current flow. So even if you have just a little couple of electrons will make it through and you'll end up not really dropping anything because you're not really testing it, because remember the switch is off, there's no actual current flow. Now when we close the switch, remember, boom, closed. Now you have a lot of electrons trying to go through the fuse, and that's when it would get the 12 volt drop. And the reason why was if you were to picture this fuse drawn as a wire, here's one single strand. That single strand of wire could really have no voltage drop because there's like just no real amount of cars on there. However, if you were to try to send a whole bunch of cars through, it would get hot, and it would actually, you'd find it's not a real good connection. It was a very spotty connection. Now, what we really want in a wire or in a conductor, such as a fuse as well, is a whole bunch of strands. See all these strands? There's all these strands. This can handle a lot of amperage. If you were to have a wire that were to be corroded, maybe even cut, but just one tiny strand right there, this would pass a resistance test. This fuse passes a resistance test. This fuse even passes a voltage drop test as long as the switch is off. But the second you start to try to flow, you realize all these strands inside are broken, and the only thing holding it is one tiny little strand right there. That's a bad fuse, or that's a bad wire. That's a bad conductor in general. But the only way that you're going to find it is if you put load on it. You put this system under load and it tries to actually flow a measurable amount of amps. Then it'll drop the voltage. Cool, so this does happen with wires, and this is part of the reason that the resistance test is not the best, and that's why we put so much emphasis on the voltage and the voltage drop test, because you actually saw it totally unplanned in a random chance. The way I'll translate this to be like health related, if let's say this is a patient and this patient may have, clogged arteries, if you tested the patient's blood pressure, their blood pressure was okay. But that's because they're just sitting there doing nothing. If you were to put this patient on a treadmill and test it under load, carrying a lot of blood, really working, you notice, oh gosh, we got a major artery problem here, like a super clogged artery. So testing the system dynamically with the lights on and everything, using voltage, is the way you find issues like this. Testing resistance or testing it with the switch off is not how you find a problem. Cool, so how that works on a car, let's just say, walk over to this engine. If we had this AC compressor clutch and this wire had just that one tiny strand, if you were to measure the resistance, you think it's good, but then you'd plug it back in and the compressor clutch still wouldn't work, and you'd be like, well, the wire's good. Well, is it? I mean, the only correct way to really test this would be to turn the AC compressor clutch on and see your available voltage here. If you're testing it with the system not under load, one tiny little strand of wire can make you think the wire's good. So again, test it dynamically. And with that, this lesson's over, and we're on to part 2 next time.